Hello there, and welcome to Science for Sleep, where curiosity takes its time and science drifts softly through the night. Tonight, we're floating a little farther from home, not in search of dreams exactly, but of distance. The kind of distance that makes you feel small in the most comforting way. You and I right now are resting inside a galaxy, a spiral of light, dust and quiet motion we call the Milky Way. It's our cosmic address, though we rarely stop to think about what that means. The stars above you tonight, faint as whispers, are not scattered randomly. They're part of an enormous structure spinning gently through space, and somehow you're sitting in the middle of it, breathing, listening, alive on a planet that calls this galaxy home. When you look up at the night sky, how far do you think you're seeing? A few stars, a few constellations maybe, a band of milky light stretching across the darkness. Every speck you can see without a telescope lies within our galaxy. Every glimmer belongs to this single island in the cosmic sea. And yet, that island is only one among hundreds of billions scattered through the universe. It's like realizing the ocean you thought was endless is actually just one drop in a storm of infinity, comforting in its immensity, humbling in its quiet. Before we wander too far from the familiar, I wonder, where are you listening from tonight? Is it late where you are? Maybe the hum of your city has faded to a low murmur, or the world outside your window is still awake. Maybe you're lying in bed, letting your thoughts slow just enough to catch this voice. Wherever you are, that's your corner of the Milky Way. That's where your light is shining back into the cosmos. Every person listening right now is part of this same galactic swirl, even if we're scattered across time zones and continents. You could say we're all tucked beneath the same cosmic blanket, though our clocks don't always agree on what time it is. If this kind of quiet curiosity helps you wind down, if you find it soothing to drift through the universe before sleep, you could gently tap like, or maybe subscribe so this little space for stillness can find others who need a pause too. It helps this channel grow, and it helps keep this calm corner glowing in the digital dark. So take a slow breath. Let your shoulders drop. The stars won't rush us. We have all the time we need to move through this story. Tonight, we're going to see how large the Milky Way truly is, how it fits into the grand pattern of the universe, how far it stretches, and how much farther everything else goes beyond it. It's not just a question of size. It's a way of understanding where we stand in the great unfolding of space itself. When you picture the Milky Way, maybe you see that wide, luminous band you've spotted on a clear summer night. It looks like a faint river running through the dark, and for much of human history that's all anyone knew it to be. A mist, a smear of light. The ancient Greeks called it the Galaxias Kyklos, the Milky Circle. They imagined it was the milk of a goddess spilled across the heavens. For millennia, no one could truly know what they were looking at. It wasn't until the early 20th century that we understood this band of light wasn't the whole universe. It was just one galaxy among many. And yet, for all our technology, for all our satellites and telescopes and equations, the size of the Milky Way still feels impossible to hold in your mind. You can list numbers, 100,000 light years across, maybe 200,000 if you count the faint outer halo. But what does that even mean to a mind that measures distance in meters and miles? A light year is the distance light travels in 1 year, nearly 10 trillion kilometers. So when we say the Milky Way is 100,000 light years wide, we're saying that if you could travel at the speed of light, it would still take you 100,000 years to cross from one edge to the other. That's longer than human history itself, longer than civilization, longer than language. Try to imagine that for a moment. You're standing in a vast plain of stars that stretches farther than the mind can track. Every single one of those points of light might have planets orbiting it. Some could have their own suns, their own moons, maybe even their own skies. And all of it belongs to one galaxy. Ours. The Milky Way is a spiral, but not a flat one. It has a disk, thick in the middle and thinner at the edges, wrapped in graceful arms of gas and dust. It rotates slowly, taking about 200 million years to complete one turn. That means since the dinosaurs vanished, our solar system has only made a single full trip around the galactic centre. The galaxy itself holds at least 100 billion stars, maybe as many as 400 billion, depending on how you count. Between those stars is an ocean of dust and invisible matter, dark matter, something we can't see, but know must be there because its gravity holds everything together. Without it, the galaxy would fly apart. It's strange to think that most of our galaxy is made of something we can't even detect directly. The visible part, all the stars and gas and glowing clouds, is only a small fraction of what truly exists. If you could look at the Milky Way from the outside, from far enough away that the whole thing fit into view, you'd see a flat spiral disk with arms curling gracefully around a glowing centre. But we can't step outside our galaxy to take that picture. We live inside it, near the edge, in one of its quieter suburbs. It's like trying to map a forest while standing between the trees. You can't see the whole shape, only hints of its pattern from the way the stars are arranged. That's why it took us so long to understand what the Milky Way really looks like. We've had to piece it together from the light that reaches us, light that has travelled for tens of thousands of years just to brush against our eyes. Even now, with all our technology, there's mystery in the details. We know it's a barred spiral galaxy, meaning it has a central bar of stars running through its core before the arms spiral outward. We know our Sun sits in a small arm called Orion's Spur between two major arms named Sagittarius and Perseus. We know the disk of the galaxy is about 1,000 light-years thick, though it bulges in the middle where stars are densely packed. But beyond those measurements, the Milky Way remains an idea built from light. We've never seen it whole, and that's where the scale starts to drift beyond comprehension. Our galaxy is vast, but it's not alone. The Milky Way shares the cosmic neighbourhood with dozens of smaller satellite galaxies. The large and small Magellanic Clouds are the most famous. They orbit us like quiet companions, each with its own population of stars. Farther away there's the Andromeda Galaxy, our nearest large neighbour, heading toward us on a slow collision course that won't reach its dramatic finale for another 4 billion years. When it does, the two galaxies will merge, forming something new, larger, calmer, and likely elliptical in shape. But before we drift too far toward the future, let's stay in the present, inside our own swirling home. Imagine drifting upward, slowly, as if you could rise through the dark until you were floating above the disk of stars. You'd see billions of suns scattered like sparks, some blue and new, some red and old. Between them, thin lanes of dust trace the spiral arms, absorbing light and re-emitting it as a soft infrared glow. Farther still, faint globular clusters, ancient gatherings of stars, hover in the halo around the galaxy, relics from its earliest days. The whole structure turns slowly, elegantly, anchored by a hidden mass at its heart, a supermassive black hole known as Sagittarius A. That black hole, millions of times the mass of our Sun, is completely invisible, yet it shapes everything around it. Stars orbit it at incredible speeds, drawn by gravity so strong that even light can't escape. If you could watch it closely, you'd see gas swirling toward it, heating up until it glows. But from here, it's just another point in the dark, a quiet engine keeping the galaxy in motion. Our galaxy's story is not unique. Across the universe there are countless others, some smaller, some larger, some older, some still forming. Some are elegant spirals like ours, others are massive elliptical clouds, or irregular clusters twisted by collisions. They gather in groups, then clusters, then vast webs stretching through the cosmos. Compared to all of that, the Milky Way is just one ordinary member of a much greater pattern, yet there's comfort in its ordinariness. The same physics that governs our galaxy governs them all. The same stars that burn here burn elsewhere. The same forces shaping our world shape worlds we haven't even seen. And somewhere out there, perhaps in another spiral arm, another being might be wondering the same thing we are tonight. How big is all of this really? How far does it go? How can something so immense hold something as small and fleeting as a thought? You might notice how your sense of scale begins to blur. That's part of the journey. The farther we look, the more we realize that our measurements, kilometers, years, even light years, start to lose meaning. Numbers become too large to carry comfortably. So instead, we rely on comparisons. The Milky Way is vast, but the space between galaxies is even vaster. The universe stretches beyond what any telescope can see, and every time we look deeper, we find more galaxies, more light, more mystery. When you think about it, asking how big the Milky Way is compared to the universe is a bit like asking how big a single wave is compared to the ocean. You can measure it, yes, but the beauty lies in knowing that it's part of something endlessly larger, endlessly moving. The galaxy isn't isolated. It's part of the grand flow of cosmic evolution. Stars forming, burning, dying, scattering elements that will one day form new stars, new worlds, perhaps new listeners lying awake, wondering where they are in all this. For now, we're just beginning our quiet exploration. We've set our perspective. We know where we are, roughly at least. A small solar system orbiting a star, halfway down one spiral arm, drifting at 200 kilometers per second around a galactic center, we'll never see with our own eyes. It's enough to make you feel both tiny and infinite at once. And as we move deeper into this story, we'll trace that scale outward, from our home in the Milky Way to the immense structures that bind the universe together. You live inside a galaxy that doesn't feel like a galaxy. It doesn't shimmer above you like a perfect spiral or appear as a neat collection of arms and clusters. From the ground, it's simply the night sky, quiet and scattered, a soft sprawl of dots stretching from horizon to horizon. That's how home looks from the inside. When you live within something so vast, it hides itself. We see the Milky Way not from the outside, but from the middle of one of its arms, peering sideways through its glowing disk. What appears as a faint white river above you is the combined light of hundreds of billions of suns, most of which you will never see as separate points. Their light has travelled for thousands of years just to arrive here, landing on your retinas as a shimmer in the dark. Every clear night, you're looking into the structure of your own galaxy without even realizing it. To understand where you are, picture a massive, flat spiral of stars about 100,000 light-years wide. Imagine it as a disk so large that if you could shrink it down to the size of your country, our entire solar system would be smaller than a grain of sand lying somewhere near the edge. That's roughly where we are, far from the crowded core, comfortably nestled in a quieter region called the Orion Arm, or sometimes Orion Spur, a smaller branch between two of the Milky Way's main arms. Here, the stars are spaced far apart, giving our Sun and its planets room to orbit undisturbed. That space is not empty, though. It's filled with clouds of hydrogen gas, drifting dust and dark matter that makes up most of the galaxy's invisible mass. The Milky Way is not a static thing. It turns, slowly but continuously. Every star, including the Sun, moves in orbit around the galactic center. Our solar system completes one revolution roughly every 230 million years. That means since the earliest dinosaurs walked the Earth, our Sun has only completed one full lap around the galaxy. The galaxy itself, meanwhile, is drifting through space, part of a much larger network of motion we'll eventually reach. But for now, it's enough to rest in the idea that everything you've ever known, the Earth, the Moon, every moment of human history, is travelling together, carried gently through the Milky Way's gravitational tide. If you could rise above the galaxy and see it from afar, it would resemble a vast whirlpool of light. 4 main spiral arms, each thick with stars, gas and nebulae, curl around a dense central bulge. The core glows with the combined radiance of billions of older stars packed tightly together, surrounding a black hole called Sagittarius A, which anchors the whole system. Around the flat disk of the galaxy is a halo, a faint sphere of ancient stars and clusters that orbit slowly, some of them leftovers from galaxies the Milky Way long ago absorbed. Even farther out is the dark matter halo. invisible yet enormous, its gravity extending well beyond the region where any light can reach. It's that unseen mass that keeps the galaxy bound, preventing it from flying apart as it spins. When you think about the galaxy as home, it's easy to imagine it as a kind of cosmic city. At the centre lies the old district, dense and bright, where stars are packed so closely that their light merges into a golden haze. Closer to the edges, the spiral arms stretch out like highways, each filled with the younger stars and nebulae that act as cosmic nurseries. Between those arms, vast lanes of dust cast shadows across the light, forming the dark streaks you can see on a clear night. Here in our quiet neighbourhood, the star density is low enough for planets like Earth to exist in relative safety, far from the intense radiation and gravitational chaos of the core. We live, quite literally, in the suburbs of the Milky Way. The name itself, the Milky Way, has ancient roots. Every culture that looked up at the night sky gave it a story. The Greeks saw milk from the goddess Hera spilled across the heavens. The Romans kept the name. In China, it was called the Silver River. The Maori called it the Long Fish. The Maya saw it as a celestial road or a great river dividing the sky. To all of them, it was both a boundary and a bridge, a feature of the heavens that suggested direction, movement, and mystery. It's strange to think that for most of human history, no one realised this faint band of light was made of stars. Even Galileo, when he first turned his telescope toward it in 1610, was astonished to see countless pinpoints of light where the naked eye saw only mist. From that moment onward, our sense of home began to expand. The more powerful our instruments became, the more we realised how immense the Milky Way truly is. The modern estimate places its diameter at roughly 100,000 light-years, though new observations suggest it could be closer to 200,000 when you include the faint halo of stars surrounding the disk. Its thickness, near the centre, reaches about 10,000 light-years, but near our position, the disk narrows to about 1,000. Within that volume are hundreds of billions of stars, trillions of planets, and uncounted clouds of gas and dust. It's not just a single structure, it's a vast ecosystem of matter and energy, constantly in motion. Our solar system orbits roughly 26,000 light-years from the galactic centre, moving at about 220 kilometers per second. That sounds impossibly fast, yet the galaxy is so vast that even at that speed, the journey around takes hundreds of millions of years. Everything moves, but nothing seems to hurry. Space itself feels patient, as if time runs differently on that scale. To us, a century feels long. To the galaxy, it's less than a blink. The stars you see tonight may have already burned out, their light still crossing the gulf of space long after their fires have faded. If you could drift closer to the centre, you'd find the view changing. The light grows dense and golden. Clouds of gas swirl around the core, illuminated by young hot stars. The gravitational pull there is immense, and orbits become unstable. It's a place of extremes: star formation, radiation, and the silent gravity well of Sagittarius A, a black hole about 4 million times the mass of our Sun. We can't see it directly, but we can observe its influence. Stars near the centre whip around it at thousands of kilometers per second, tracing invisible ellipses that reveal its presence. Without that central mass, the galaxy's structure wouldn't hold together as it does. Farther from the core, the spiral arms stretch outward in vast curves. Within these arms, new stars are born in clouds of hydrogen gas. When enough matter collapses under gravity, it ignites, forming a new sun. Around it, dust gathers to make planets, moons, and asteroids. Somewhere in one of those clouds, billions of years ago, our own sun was born, likely from a cloud enriched by older stars that had lived and died before it. Every element in your body, carbon, oxygen, calcium, iron, was forged in those earlier generations of stars. The galaxy is not just home to stars, it is the machine that recycles matter, turning death into new beginnings again and again. Between the spiral arms lie darker regions called interarm spaces. They aren't truly empty, but they hold less gas and fewer young stars. In these quiet stretches, older stars drift more slowly, and dust is thin enough that distant light can pass through. The Milky Way's shape, if you could trace it in motion, would look like a gentle wave, bending slightly up and down. That's because the disk itself isn't perfectly flat. It warps and ripples as gravitational interactions with nearby dwarf galaxies tug on its edges. Even something as large as the Milky Way bends and flexes like a living thing. Surrounding this disk is a halo of old stars and globular clusters, spherical collections of tens of thousands or even millions of stars bound tightly together. These clusters are among the oldest objects in the galaxy, remnants from its earliest formation more than 10 billion years ago. They orbit far from the plane of the disk, slowly looping through the halo in elongated paths. Some of them may even be the remains of smaller galaxies that merged with the Milky Way in the distant past. That's one of the galaxy's quiet secrets. It has grown not just by forming new stars, but by consuming its neighbours. Over billions of years, the Milky Way has absorbed many smaller systems, pulling them apart and blending their stars into its own structure. When astronomers map the stars and gas of the Milky Way, they rely on many kinds of light: visible, infrared, radio, and X-ray. Each wavelength reveals something different. Infrared light can pierce through the dust that blocks our view in visible light, showing the shape of the arms and the glow of hidden stars. Radio waves reveal clouds of hydrogen gas stretching far beyond what we can see. X-rays expose energetic events, exploding stars, black holes feeding on matter, the fierce activity at the galactic core. When you combine all those views, you begin to see the Milky Way not as a flat band of stars, but as a living, changing system, full of turbulence and order at once. The stars within it are not scattered randomly. They form patterns, clusters, and associations that trace the galaxy's structure. Some stars travel alone, others remain bound in pairs or groups. Massive stars live fast and die young, burning out in a few million years, while smaller ones like our Sun can live for billions. The death of those large stars creates supernovae, spreading heavy elements back into the interstellar medium. That material becomes the seed for the next generation of stars. In this way, the Milky Way renews itself. Every atom of oxygen you breathe, every molecule of calcium in your bones, once belonged to a star that lived and died somewhere in this same galaxy. If you could stand far enough away to see it all at once, the Milky Way would appear serene, a soft spiral glowing against the black. But from within, it's full of motion and energy. Clouds collapse, stars ignite, others die. Radiation streams across space, magnetic fields twist through the gas. It's a dynamic environment, but one that operates on scales so vast that we perceive it as timeless. The galaxy you see tonight is not the same as it was when its light began its journey. It has already changed, evolved, shifted in ways we can barely measure. We're always looking at its past, never its present. Thinking of the Milky Way as home might seem strange. It's not a place you can visit or see in one glance, but in a sense, it's the truest definition of home we have. Every element, every planet, every cell in your body belongs to it. You're made of its materials, bound by its gravity, travelling through its space. The same atoms that once drifted between stars are now part of you, listening to this, thinking, breathing. And long after you're gone, those atoms will return to the galaxy, to be used again in some new form. The Milky Way is not just where we live, it's what we are. When you look at it that way, the galaxy feels less like a distant spectacle, and more like an enormous body of which we are a small, conscious part. The Earth orbits the Sun orbits the galaxy, and the galaxy itself moves through the greater universe. Pulled by the gravity of unseen structures, everything is connected by motion, by light, by the invisible threads of gravity stretching across billions of kilometers. The stars we see tonight are not fixed points. They are companions travelling with us on this endless journey around the centre. Each one follows its own path, yet together they create the shape we call home. As the night deepens and the sky turns overhead, you can almost feel that motion. Not the spinning of the earth beneath you, though that too is part of it, but the slower, grander movement of everything drifting through space. The Milky Way is not still. It's a river of stars flowing across the universe, carrying us quietly within it. Somewhere deep in its heart, gravity keeps the rhythm, and every orbit, every turn is another verse in the story of home. You can picture the Milky Way now as a spiral disk of stars, wide and bright and full of quiet motion. You can imagine the way it curves, the way its light looks when seen from the edge of a world like ours. But knowing what it looks like and knowing how large it is are not the same thing. Measuring something that enormous, something we can't step outside of to see, requires patience and creativity. It also requires a sense of humility, because every measurement of the cosmos is really a measurement of our ability to understand it. To measure the Milky Way is to measure the limits of our sight. Humans have always tried to give the sky a shape. Ancient astronomers marked the movement of planets against the fixed stars and thought the heavens might be a dome. The idea of a galaxy came much later, when the telescope showed that the misty band above was made of uncountable stars. Even then, it wasn't obvious how far away they were. The problem of distance haunted astronomers for centuries. When you look at a star, it doesn't come with a label telling you how far its light has travelled. All you have is brightness, colour, and the faint clues hidden in the light itself. The first real measure of cosmic distance came from an idea called parallax. You can see it with your own eyes if you hold out your finger and close one eye, then the other. Your finger seems to shift against the background. The closer your finger, the bigger the shift. Astronomers use the same trick on a much larger scale. They measure how a nearby star's position appears to change against the more distant stars as the Earth moves around the Sun. The angle of that shift is tiny, measured in fractions of a degree, but from it you can calculate the distance. When this method was first used successfully in the 19th century, it opened the universe a little wider. Suddenly, the stars weren't fixed lights on a sphere. They were suns scattered through space at immense distances, some hundreds or thousands of light years away. The Milky Way began to grow in our minds. Parallax works well for nearby stars, but only to a point. Beyond a few thousand light years, the angles become too small to measure from Earth. To reach farther, astronomers needed new yardsticks. They found one in a kind of star called a Cepheid variable. These stars pulse in brightness with a regular rhythm, and the rate of that pulse is linked to their true luminosity. Measure the period of the flicker, compare it to how bright the star appears, and you can tell how far away it is. This discovery, made in the early 20th century, allowed astronomers to measure distances across the entire galaxy. It also revealed something unexpected. There were other galaxies beyond ours, each full of its own stars. What we had thought was the entire universe was only one spiral among billions. Inside the Milky Way, mapping distance became a kind of detective work. Light itself is the clue, but it's not always straightforward. Dust between the stars scatters and absorbs light, making distant stars look dimmer and redder than they are. Radio waves, which can pass through dust, revealed another layer of structure. When astronomers pointed radio telescopes at the sky, they detected hydrogen gas spread throughout the galaxy. The pattern of that emission traced the spiral arms, letting us see through the dust that hides the Milky Way's shape from ordinary view. Later, infrared and microwave telescopes would add even more detail, showing that our galaxy is larger and more complex than we ever guessed. Even with all these tools, measurement in astronomy is rarely direct. Everything we know about the galaxy comes from interpreting light, from understanding how matter emits, absorbs and shifts it. When a star orbits the galactic center, its motion changes the wavelength of the light it sends us, a small shift called the Doppler effect. By measuring those shifts, astronomers can map the motion of stars and gas, revealing the mass and rotation of the galaxy. It's like listening to an orchestra and figuring out where each instrument is based on the pitch and timing of the notes. The pattern tells you the structure, even if you can't see every musician. These measurements showed something strange. The outer parts of the galaxy rotate faster than they should, given the visible mass. According to Newton's laws, the stars at the edge should move more slowly, but they don't. The simplest explanation is that there's more mass than we can see. Dark matter. Whatever it is, it doesn't emit or absorb light, but it exerts gravity. It forms a vast halo that surrounds the visible disk, making the Milky Way far more massive than we once thought. So in a way, measuring the galaxy meant discovering that most of it is invisible. Our instruments told us that we were seeing only a fraction of what exists. Every advance in measurement changed our sense of size. When the first star distances were measured, the Milky Way seemed almost infinite. Later, when we mapped it with Cepheids and radio telescopes, it became something we could describe in numbers. Hundreds of billions of stars, 100,000 light-years wide. Each refinement shrinks the mystery but never removes it entirely. Beyond every new estimate lies more uncertainty, more layers we can't quite reach. The farther we look, the more the universe stretches beyond our methods. Astronomers have built elaborate ladders of distance, each rung relying on the one below it. Parallax for nearby stars, variable stars for distant ones, supernovae for galaxies farther away. Each method extends the reach, but each carries error. To measure the galaxy is to balance on that ladder, aware that a small uncertainty in one rung ripples through the rest. Even the value of a light year depends on how precisely we know the speed of light, and even that constant is measured within limits. Science often works this way, layered estimates built from careful but imperfect observations. Yet from those imperfections, a coherent picture emerges. Think about what a light year means for a moment. Light travels nearly 300,000 kilometers every second. Multiply that by the number of seconds in a year, and you get a distance so vast that it becomes abstract. It's easier to say that light could circle the Earth more than 7 times in 1 second, or that it takes about 8 minutes to travel from the Sun to us. A light year is the distance that same beam of light covers in a year of those seconds, over 9 trillion kilometers. When we say the Milky Way is 100,000 light-years wide, we're saying its light takes 100,000 years to cross from side to side. Every measure we take of the galaxy is a measure through time as well as space. There's a quiet irony in that. When we measure a distant star, we're not seeing it as it is now, but as it was when its light began the journey. A star 10,000 light-years away is being seen as it was 10,000 years ago. The map of the Milky Way is also a history, a record of what used to be. When we look toward the galactic center, we see light that started its trip long before modern humans existed. Measurement becomes memory, a reconstruction of a living system frozen at different moments along the path of light. All of this means that when you hear a number, 100,000 light-years, 200 billion stars, it's not a fixed truth. It's an approximation built on light, motion, and math. Astronomers debate the exact figures constantly. Some estimates put the Milky Way's diameter closer to 120,000 light-years, others stretch it farther. The number of stars could be as low as 100 billion or as high as 400 billion. Each value depends on models of how stars are distributed and how much hidden mass lies beyond the edges we can see. Measuring something this vast is like trying to measure the ocean with a cup. You can only sample it, then infer the rest. Yet even with its uncertainties, the process reveals something beautiful about how science works. It's not about having a final answer, it's about refining the picture again and again. Every new telescope, every improved detector adds clarity. The Gaia satellite, launched by the European Space Agency, is currently measuring the positions and motions of over 1 billion stars in the Milky Way with unprecedented precision. Its data are reshaping our understanding of the galaxy's structure, showing subtle ripples, asymmetries, and patterns that hint at past collisions with smaller galaxies. Each update doesn't just give us numbers, it gives us history. It tells us where the Milky Way has been and where it's going. Even the way we visualize the galaxy depends on measurement. Artist impressions of the Milky Way, the graceful spirals, the glowing core, are built from data and models. No one has ever seen it from the outside. Our entire picture is a reconstruction based on angles, brightness, and motion. It's astonishing that we can form such a clear image from so few direct observations. Measuring the immeasurable becomes a kind of art, one grounded in equations but guided by imagination. For all our instruments, there remains something profoundly human about it. The urge to measure is really an urge to belong. When we measure the galaxy, we're asking where we fit within it. We're translating awe into numbers so we can hold it in our minds without being overwhelmed. And yet, no matter how precise the figures become, there's always that sense of something slipping just beyond reach. Something too large, too far, too faint to quantify. The numbers give us structure, but the wonder fills the gaps. As our instruments extend their reach, we start to see the Milky Way not as a flat map, but as a three-dimensional space with depth and motion. Stars rise and fall through the galactic plane, the disk itself undulating like a slow wave. Streams of stars trace the paths of long-ago collisions. The galaxy is not a static shape, but a history of movement recorded in light. Measuring it is like measuring the wind. You can track its flow, describe its effect, but you never quite capture it. And even as we map every corner we can, there's still the question of scale beyond the galaxy. Once you know the size of the Milky Way, the next question follows naturally. How large is the space it sits in? What lies beyond its edges? To compare the Milky Way to the universe, we need to measure not just our own island of stars, but the ocean that contains it. That requires a different kind of yardstick, one that stretches far beyond parallax or Cepheids. It involves the redshift of galaxies, the expansion of space itself, the faint afterglow of the Big Bang. Those measurements take us from local distances to cosmic ones, from the map of our home to the architecture of the universe. Before we reach that scale, it's worth pausing on what measurement really means in this context. It isn't about claiming certainty. It's about constructing a bridge between perception and reality. We can't touch the galaxy, but through careful observation, we can translate its light into distance, motion, and mass. Each measurement, no matter how small, connects us to something far larger. It's proof that we can look into the dark and bring back understanding. When you listen to numbers about the Milky Way, the light years, the masses, the velocities, they can feel abstract, but they're all built from the same principle. Light travels, and in that travel it carries information. Every photon arriving at your eye or at the mirror of a telescope is a messenger from somewhere in the galaxy. Measuring the immeasurable is simply learning to read those messages, to decode the faint stories written in Starlight, and those stories continue. Each new mission refines the measurements, reshapes the map, extends the horizon. We'll never see the entire Milky Way directly, but with every step our mental image becomes more complete. The numbers may shift, but the pattern remains, a spiral of stars vast and luminous, held together by gravity and time. Through measurement, we transform mystery into knowledge, even if that knowledge only deepens the sense of wonder that made us measure in the first place. From here, the questions will only grow larger. If this one galaxy spans 100,000 light years, how far apart are the next ones? How many galaxies are there? How big is the space that contains them all? When you look at the night sky, what you see is light. Nothing more, nothing less. Every idea we have about the Milky Way, every distance, every map, every photograph of galaxies far beyond our own, all of it comes from studying light. It's the only messenger that reaches us from the vast distances of space. The universe doesn't send sound, it doesn't send touch, it sends light. And through it, we've learned to read the story of where we are. The Milky Way, invisible as a whole to our eyes, becomes knowable through the patient decoding of that light, one wavelength at a time. Light moves at a fixed speed, but it's not uniform in how it reveals itself. To the human eye, only a small slice of the electromagnetic spectrum is visible, a range so narrow that it's almost comically small compared to what exists. Beyond red light lies infrared, beyond that microwave, then radio waves, stretching to enormous wavelengths. On the other side of the visible range, beyond violet, there's ultraviolet, then X-rays, then gamma rays, wavelengths shorter and shorter, until they become unimaginably energetic. The Milky Way glows in all of them. If we could see across that entire spectrum at once, our galaxy wouldn't look like the smooth, pale ribbon we see from the ground. It would be a complex tapestry, with each type of light revealing something different about its structure and history. The visible band, the one our eyes evolved to recognize, is dominated by starlight. When you look up and see that faint milky glow stretching across the sky, you're seeing the combined light of billions of stars packed so closely together that they blur into a luminous haze. But that's only the surface of the story. Much of the Milky Way is hidden behind thick lanes of dust. In visible light, those regions appear as dark rifts where no stars seem to shine. For centuries, astronomers thought these were empty spaces. It wasn't until the development of infrared telescopes that we realized the darkness was an illusion. The dust wasn't a void. It was the birthplace of stars. Infrared light can slip through dust that blocks visible light. When astronomers began using infrared detectors to observe the sky, they saw through the dark bands of the Milky Way and found vast clouds of gas and dust glowing faintly with heat. Inside those clouds, gravity was pulling material together, forming new stars and planetary systems. The Milky Way, which had seemed like a static pattern of ancient light, turned out to be alive with creation. Every dark patch hid the potential for thousands of suns yet to be born. As technology improved, we learned to see the Milky Way in radio waves. In 1951, astronomers detected radio emissions from hydrogen atoms, the most abundant element in the galaxy. Hydrogen naturally emits a faint signal at a wavelength of 21 centimeters. That discovery changed everything. Using radio telescopes, scientists began mapping hydrogen throughout the Milky Way, tracing its spiral arms and revealing its true shape. What had once been impossible, seeing the structure of our own galaxy from within, became achievable through the language of radio light. Those observations show that the Milky Way has 4 main spiral arms, winding outward from the central bar, each one rich with gas, dust, and young stars. Radio astronomy also unveiled structures invisible in other forms of light. Immense clouds of hydrogen extending far beyond the visible disk, filaments stretching between arms, remnants of ancient collisions. Some of these structures move at unexpected speeds or directions, hints of interactions with smaller galaxies or clouds falling into the Milky Way from intergalactic space. Every new wavelength adds another layer of information, another way to read the galaxy's long and complex story. X-ray and gamma-ray telescopes revealed yet another aspect of the Milky Way, its violence. In these high-energy wavelengths, the calm spiral we see in visible light transforms into a chaotic landscape of explosions, collisions, and radiation. Supernova remnants glow fiercely. Black holes and neutron stars emit flashes of X-rays as they consume matter, and the galactic center shines with bursts of energy from the region around Sagittarius A, the supermassive black hole at the core. These forms of light, invisible to our eyes, show that the Milky Way is not a quiet place. It's a constant interplay of creation and destruction, of stars being born, living and dying across millions of years. Each wavelength gives a different version of the galaxy, like instruments in an orchestra playing the same symphony in different tones. Combine them, and the Milky Way becomes a complete dynamic system, not a flat picture, but a living, breathing structure. That's what modern astronomy does. It listens to the light in all its forms and reconstructs reality from the harmony of signals. When you look at the stars yourself, your eyes act as small telescopes. They gather photons that have been travelling for years, decades, sometimes thousands of years. Each photon carries a record of where it came from, its colour, its energy, its direction. If you could analyse that information, you could tell what kind of star it came from, what elements are present in that star's atmosphere, even whether the star is moving toward or away from you. That's the power of light. It's both messenger and measurement. Spectroscopy, the study of how matter interacts with light, became the tool that transformed astronomy from wonder into science. In the 19th century, when scientists first split starlight into its component colours using a prism, they saw dark lines cutting across the rainbow. Those lines corresponded to specific elements, each one absorbing light at certain wavelengths. The same pattern seen in a laboratory flame matched the pattern in starlight. That realization meant that the stars are made of the same elements found on Earth: hydrogen, helium, carbon, oxygen. The universe was built from the same ingredients everywhere. The Milky Way, in all its immensity, was not composed of something foreign or unknowable. It was made of the same matter we find here, under our feet. By measuring how those spectral lines shift toward the red or blue end of the spectrum, astronomers can also tell whether a star is moving away or toward us. The amount of shift tells us its speed, a direct application of the Doppler effect. When you map those motions across thousands of stars, patterns appear: the rotation of the galaxy, the streaming of stars along the arms, the gravitational pull of unseen masses. The Milky Way becomes not just a picture, but a moving structure, a place with depth and flow. Even with all this information, the Milky Way remains partly hidden. The dust that obscures our view in visible light is pervasive, and while infrared and radio waves can pierce it, they have limits. That's why astronomers turn their instruments upward, beyond Earth's atmosphere. Space telescopes like Hubble, Spitzer, and now the James Webb Space Telescope see the sky without interference from air or weather. From orbit, the view of the Milky Way expands dramatically. Hubble revealed the fine details of nebulae, the swirling clouds where stars are born. Spitzer showed the glow of dust heated by newborn suns. The Webb telescope, operating in the infrared, peers even deeper, tracing the earliest light that escapes from behind thick veils of gas. The more we've learned to see, the more the galaxy has transformed from a static image into a process. The Milky Way isn't a fixed shape, it's a continuous act of change. Stars form, shine, and die, scattering heavy elements into the interstellar medium. Those elements collect, form new clouds, and the cycle begins again. In that sense, the galaxy is a kind of luminous ecosystem, sustained by the constant recycling of light and matter. The photons that reach us tonight are part of that cycle, the end of a journey that began long before the Earth existed. Light also gives us a way to measure time. Because it travels at a constant speed, distance becomes time's twin. When we say a star is 10,000 light years away, we're also saying we see it as it was 10,000 years ago. The Milky Way is not just a structure in space, it's a record through time. Each point of light is a different chapter of its history. When we map it, we're mapping the past as well as the present. The faintest light we detect comes from stars near the edge of the galaxy, where the density of matter thins into intergalactic space. Some of that light is so old that it carries memories of the galaxy's formation, when smaller protogalaxies merged to create the spiral we inhabit now. In the halo surrounding the Milky Way, ancient stars orbit slowly, some with chemical compositions that mark them as survivors from those early times. Their light tells us what the galaxy was made of before generations of stars enriched it with heavier elements. By studying that light, we trace the Milky Way's ancestry, like archaeologists sifting through layers of cosmic sediment. In the end, everything we know about our galaxy, and everything we will ever know about the universe, depends on light. It's our only connection to the vastness beyond. We can't travel to the stars, not yet, but their light travels to us. It crosses the emptiness at incredible speed, carrying all the information we need to piece together a map of reality. Each telescope, each detector, is just another way of catching that light and listening to what it says. If you step outside on a clear night and let your eyes adjust, you'll see a sky that has been mapped for thousands of years. But now you can know what those points of light represent. You're not just looking at beauty, you're looking at data, at the evidence of motion, temperature and distance. The light from Vega left 25 years ago. The light from Deneb began its journey almost 2,000 years ago, before the fall of Rome. The light from the Galactic Center has been travelling for more than 25,000 years. Every star you see is a mixture of now and then, a collection of moments stretched across time. Light doesn't just show us where we are, it reminds us that seeing the universe means looking back through history. When you gaze at the Milky Way, you're witnessing an ongoing event that has already happened. The stars you see are still there, but not as you see them. Some are older, some may already have burned out. The image above you is a projection of many paths layered together. It's a beautiful illusion, but one that contains real knowledge. And so, when astronomers say they map the sky, what they're really doing is gathering time. They're taking light that has travelled across millennia and arranging it into patterns we can understand. Each observation, each line of data, each image is a tiny piece of a vast, luminous puzzle. When it's assembled, we get something remarkable. Not just a map of stars, but a map of how the universe tells its story through light. At the centre of the Milky Way, there is a region we can never visit. A place so dense and powerful that it bends light itself. It doesn't shine, yet it anchors everything we see. The stars orbit it, the spiral arms curve around it, and the gravity it exerts shapes the galaxy's entire rhythm. That centre, hidden behind clouds of dust and gas, lies in the direction of the constellation Sagittarius. When we look that way, we're staring into what astronomers call the galactic core. There, more than 26,000 light-years from Earth, sits the Milky Way's heart, a supermassive black hole known as Sagittarius A. You can't see it directly. Even with the most powerful telescopes, what we detect is not the black hole itself, but the effect it has on everything nearby. A black hole is defined by its gravity. It's a region where matter has collapsed so completely that nothing, not even light, can escape its pull. The edge of that region is called the event horizon, the point beyond which escape becomes impossible. Inside it, the laws of physics as we know them cease to function in any familiar way. Time and space fold together, and our equations break down. Yet, despite its darkness, the black hole at the Milky Way's centre reveals itself through what happens around it. For decades, astronomers suspected that something massive must lurk at the galaxy's core. They couldn't see it, but they could track the motion of the stars near the centre. Those stars were moving at astonishing speeds, thousands of kilometres per second, in tight, fast orbits around an invisible point. The only explanation that fit the data was a compact object with millions of times the mass of the Sun confined within a space smaller than our solar system. Over time, repeated measurements confirmed it. The black hole's mass is about 4 million suns, and yet all of it is contained within a region no larger than the orbit of Mercury. That discovery confirmed what theory had long predicted. Galaxies grow around black holes, and black holes grow with them. The centre of the Milky Way isn't quiet. It's a turbulent region filled with dense gas clouds, radiation, and magnetic fields. Around the black hole is an accretion disk, a swirling ring of hot gas and dust spiralling inward. As this material falls toward the event horizon, it heats up through friction and compression until it glows with X-rays and infrared light. Sometimes, when the black hole pulls in more matter than it can swallow at once, powerful jets of energy erupt from its poles, blasting into space at nearly the speed of light. These outbursts can stretch for thousands of light years, influencing star formation far beyond the core. Though the Milky Way's black hole is relatively calm compared to the monstrous ones found in more active galaxies, traces of its power remain visible in the structures around it. In 2019, astronomers achieved something remarkable. They captured the first image of a black hole's shadow. It wasn't Sagittarius A, but a much larger one in another galaxy, M87. Using a global network of radio telescopes called the Event Horizon Telescope, scientists combined observations from across the world to create a picture showing the glowing ring of gas surrounding the darkness at the centre. 2 years later, the same method was used to image Sagittarius A cell itself. The result wasn't a crisp photograph, but a blurred, glowing ring encircling a shadow, proof that what theory described was real. The Milky Way's heart, invisible for so long, finally had a face. Seeing that image was a strange kind of revelation. It confirmed what physics predicted, but it also added something more human. For the first time, we could visualize the center of our galaxy, the gravitational anchor of our cosmic home. The light around it had traveled for 26,000 years to reach us, meaning we were seeing the black hole as it looked when early humans were carving symbols on cave walls. The time delay is part of the beauty of astronomy. Every observation is a glimpse into the past. When you look at Sagittarius A, you're seeing light that began its journey before civilization existed. The black hole's gravity affects everything near it. Stars closer to the core orbit faster, tracing elliptical paths that reveal the mass hidden in darkness. Some of those stars pass so near the centre that their trajectories curve sharply, completing an orbit in just a few years. The most famous of them, known as S2, has been observed for decades. Each time it swings near the black hole, it moves at more than 7,000 kilometers per second. Watching its orbit provides one of the best tests of Einstein's general theory of relativity, which predicts how gravity warps both space and time. The results match perfectly. The black hole isn't just a concept, it's a working laboratory for the laws of the universe. What's remarkable is how stable the galaxy remains despite that immense power. From our vantage point, life continues undisturbed, the sun follows its orbit, and the stars in our region drift calmly through space. The black hole's gravity is overwhelming only up close. At our distance, its effect is no stronger than the combined pull of the galaxy's entire mass. That contrast, between the violence of the centre and the tranquility of our position, is part of what makes the Milky Way feel so balanced. It's a system where extremes coexist, where chaos at the heart supports harmony at the edges. The region around Sagittarius A also tells the story of the galaxy's past. Surrounding the black hole is a dense cluster of stars, some newly formed, others ancient. The high density and the presence of heavy elements suggest that the galactic centre has gone through multiple cycles of star formation and destruction. Supernovae near the core have enriched the surrounding gas with metals, and collisions between stars are more likely there than anywhere else in the galaxy. Some theories propose that the central black hole itself grew through such collisions, merging smaller black holes left behind by massive stars until it reached its current size. It's easy to imagine the centre of the galaxy as silent, but it isn't. It hums with radiation, magnetic fields, and shock waves from stellar winds. The gas clouds there are dense enough to collapse into stars, but also turbulent enough to be torn apart before they do. Radio telescopes detect arcs and filaments of energy, curved lines that trace the invisible magnetic structure of the core. The entire region is alive with movement on a scale both vast and minute. What looks like stillness from our distant view is, up close, an arena of constant change. Despite its inaccessibility, the galactic centre connects us to a deeper understanding of how galaxies evolve. Nearly every large galaxy we've studied has a supermassive black hole at its centre, and the size of that black hole correlates with the size of the galaxy itself. That relationship suggests that galaxies and black holes grow together, influencing each other's development. The Milky Way's black hole may have shaped the early structure of the disk, regulating the formation of stars and maintaining the balance between expansion and collapse. Without it, the galaxy might look very different, less stable, perhaps more irregular. When astronomers simulate galaxies on supercomputers, they often find that without a central black hole releasing energy into the surrounding gas, star formation proceeds too quickly, exhausting the gas supply early. The black hole's outbursts act as a kind of feedback, heating and stirring the gas, preventing it from condensing all at once. In this sense, the black hole is both destroyer and creator, both heart and regulator. Its darkness gives the galaxy shape, its gravity provides order, and its bursts of energy sustain the balance that allows new stars, and eventually planets, to exist. Even though we can't see inside it, we can imagine what the black hole's gravity does to space-time itself. According to general relativity, the fabric of space curves around mass. Near a black hole, that curvature becomes so extreme that time slows relative to distant observers. For someone hovering just outside the event horizon, seconds would pass while millennia slipped by elsewhere. Inside, time and space switch roles in a way that defies ordinary understanding. What happens beyond that boundary remains one of physics' great mysteries. Whether matter is crushed into a singularity of infinite density or something else entirely, no one can say for sure. The equations reach a point where they simply stop giving meaningful answers. The heart of darkness is therefore also the heart of knowledge's limit. It's the place where our understanding meets the edge of what's possible to know. And yet, even that boundary tells us something profound. The fact that we can detect, measure, and model such a region at all speaks to how far human curiosity has carried us. From a small planet near the edge of one spiral arm, we've managed to infer the existence of a gravitational engine millions of times the mass of our Sun, 26,000 light-years away. We've observed its influence on the motion of stars, its emission of X-rays, and even its faint echo in radio light. We've turned darkness into data. The next time you look toward the constellation Sagittarius, remember that direction points to the galaxy's core. You won't see anything remarkable there with your eyes, just a dense field of stars against a dark background. But buried in that darkness, invisible yet inescapable, lies the force that binds the Milky Way together. Every orbit of every star, including our own Sun, traces its path under that central gravity. The entire galaxy, from the glowing core to the faint outer halo, turns around that silent point. It's strange to think of a black hole as home, but in a way it is. The Milky Way's existence depends on it. The stars that shine above you tonight owe their ordered motion to that unseen mass at the centre. The Sun's steady path, the gentle rhythm of our planet's orbit, all of it participates in a cosmic dance choreographed by gravity that began billions of years ago. We live far from the galactic centre, yet our motion is tied to it as surely as the hands of a clock to its gears. If the galaxy is a vast city of stars, then the black hole is its core, dense and ancient, where everything began and toward which everything turns. It's a place we'll never reach, but it defines the structure of everything we know. The heart of darkness isn't a void to fear. It's the quiet centre that makes the galaxy possible. And as we drift through space, carried by its gravity, we continue to learn from the light that circles it, light that maps not only our sky, but the deep architecture of the cosmos itself. Every star in the Milky Way is a sun, every single one burning on its own, complete, with light, gravity, and often planets orbiting around it. It's almost impossible to hold that fact in your mind. We talk about stars as if they were distant decorations, but each one is an entire system, a world maker. From Earth they look small only because of distance. The galaxy itself is made of them, billions upon billions arranged in clusters, streams and spirals. If you could see the Milky Way from afar, those stars would blend together into a smooth glow. From here, we can only catch the faintest fraction, the few close enough to pierce the dark with their light. Astronomers estimate that the Milky Way contains at least 100 billion stars, and perhaps 400 billion. The number is uncertain because many of the faintest stars are too dim to see even with powerful telescopes. Red dwarfs, the smallest kind of stars, make up the majority, but they're nearly invisible from Earth. They burn slowly and quietly with little light. If you could gather them all and view them together, they would outnumber the bright ones thousands of times over. The galaxy is filled with them, the silent background population that gives it mass and gravity. Comparisons help, but only slightly. Imagine standing on a beach. Pick up a handful of sand. In that handful are tens of thousands of grains, each one tiny and smooth. Now imagine that every grain represents a single star, and that your handful is only a small patch of a vast shore stretching farther than you can see. Even that image falls short. There are more stars in our galaxy than grains of sand on all the beaches of Earth. It's a number so large that it stops feeling like a number at all. It becomes a texture, something continuous rather than countable. The Sun, the star we know best, is ordinary among them. It's a medium-sized yellow star, stable and middle-aged. Its light and warmth make life possible here, but in the galactic scale, it's one of the quieter ones. Some stars are many times more massive, blazing blue-white and burning through their fuel in just a few million years. Others are small and cool, glowing faintly red for trillions of years. There are stars born in pairs, triplets, and entire clusters, gravitationally bound since their formation. There are giants that expand and contract, pulsating with internal rhythms, and white dwarfs, the dense remnants of stars that have exhausted their fuel. Every variation of size and temperature adds another shade to the Milky Way's light. The life of a star begins in darkness. Deep within clouds of gas and dust, gravity pulls material together. As the cloud collapses, it fragments into dense clumps, and each clump becomes a protostar. The process takes millions of years. When the pressure and temperature at the core become high enough, hydrogen atoms begin to fuse into helium, releasing energy. That's when a star truly ignites. The light that shines from it is the outward expression of that nuclear balance. Gravity trying to pull matter inward, energy pushing outward. As long as those forces are in equilibrium, the star endures. Our galaxy is full of these stellar nurseries. Some of them, like the Orion Nebula, can be seen with small telescopes, glowing softly with the light of newborn stars. Others are hidden behind thick veils of dust, detectable only in infrared or radio wavelengths. Within these regions, clusters of young stars form together, often numbering in the thousands. They start out close, their gravity interwoven, but over time they drift apart, dispersing into the galaxy. Some of the oldest stars we can observe still travel together in ancient groups called globular clusters, remnants of the early Milky Way. These clusters orbit far above and below the galactic plane, each one a dense sphere of tens of thousands of stars packed tightly together. When you look at the night sky, the brightness of the stars is deceptive. A bright star is not necessarily closer or larger. It might simply be more luminous. Some stars radiate thousands of times more energy than the Sun. Others, far closer to us, are so dim that we need telescopes to detect them. Distance, luminosity, and perspective all blend in a way that hides the true scale of what we're seeing. The light from even the nearest stars takes years to reach us. From the farthest edges of the Milky Way, it takes tens of thousands of years. When that light reaches Earth, it has travelled through vast interstellar spaces, shaped by magnetic fields and dust, bent slightly by gravity, scattered and sometimes absorbed, before finally arriving in your eye or in a telescope's mirror. Every star has its own system of planets, moons, asteroids, and comets. In recent decades, astronomers have confirmed thousands of exoplanets orbiting other stars, with many more waiting to be discovered. The evidence suggests that planets are the rule, not the exception. The Milky Way may contain hundreds of billions of them, scattered across its spiral arms. Some orbit close to their stars, others wander in the cold outskirts. A few may host oceans, atmospheres, or conditions that could support life. When we talk about the galaxy being filled with stars, we're also talking about the possibility of worlds, countless places, each with its own story unfolding in silence. Stars don't last forever. The balance that keeps them stable eventually tips. When hydrogen in the core runs out, the star contracts and heats up, igniting new layers of fusion. The outer layers expand and the star becomes a red giant. For stars like our Sun, this phase lasts only a short time before the outer layers drift away into space, forming a glowing shell called a planetary nebula. The core that remains cools into a white dwarf, a dense, fading ember about the size of Earth, but with the mass of the Sun. Over trillions of years, even those remnants will dim and vanish. Massive stars end their lives more dramatically. When fusion can no longer support them, their cores collapse in a fraction of a second, triggering a supernova explosion. The blast is so powerful that it briefly outshines an entire galaxy. In those final moments, elements heavier than iron are forged. Gold, silver, uranium, all created in the violent death of a star. Those elements scatter into space, enriching the interstellar medium. Later, they'll become part of new stars, planets, and living things. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was made in stars that lived and died long before the Sun was born. The galaxy, then, is a cycle of light and renewal. Stars are born, shine, die, and give rise to new generations. Each turn of that cycle builds the richness of the Milky Way. In the densest parts of the disk, where gas is abundant, star formation continues. In the outer regions, where gas is thin, stars are older, their orbits more elongated, their light dimmer and redder. The galaxy's glow as seen from Earth is the sum of all these lives, added together over billions of years. When astronomers map the stars, they find patterns that reveal how the Milky Way has grown. Streams of stars trace the remnants of smaller galaxies that were pulled in and absorbed long ago. The galaxy we live in wasn't built in one moment. It assembled over time, merging with others, collecting their stars like memories. Some of those stars still travel in long arcs around the disk, silent witnesses to collisions that happened before the Earth existed. If we could see the Milky Way without the interference of dust or distance, it would stretch across the sky in dazzling complexity. The disk would glow softly, the spiral arms would shimmer with regions of new star formation, and the central bulge would shine with the dense light of old stars. The view would be overwhelming, not because of brightness, but because of number. The galaxy isn't empty space punctuated by stars. It's a vast continuous field of suns, each one separated by light years yet bound together by gravity. The comparison to sand is helpful not only for scale but for texture. A single grain means little, but together they form landscapes, dunes, shores, deserts, each shaped by wind and time. In the same way, the stars of the Milky Way create structure through sheer abundance. Their combined light defines the spiral arms. Their collective gravity shapes the disk. Just as dunes shift and ripple, the galaxy's arms are not fixed. They're patterns that move slowly, waves of density where stars form and drift away. Over millions of years, the arms change shape, but the overall spiral remains. It's a dynamic equilibrium, always changing, yet always recognizable. The light of the stars also interacts with the gas and dust between them, creating the glowing regions known as nebulae. Ultraviolet radiation from hot young stars excites the surrounding gas, making it shine in reds, blues and purples. Some nebulae mark sites of starbirth, others are the remnants of supernovae. Together they act as signposts of stellar life cycles scattered throughout the galaxy. The Milky Way is filled with them, faint to our eyes but brilliant in photographs that capture wavelengths beyond the visible. Our understanding of the galaxy's stars continues to evolve. Space missions like Gaia have mapped the positions and motions of more than 1 billion of them with exquisite precision. The data show subtle ripples and asymmetries in the Milky Way's disk, evidence of gravitational interactions with smaller galaxies and clouds of dark matter. Even within this immense structure, the motion of stars is not random but patterned, guided by invisible forces. Each star moves along its path like a grain of sand carried by the slow current of an unseen tide. When you look at the night sky, you're seeing only the nearest stars, perhaps a few thousand visible to the naked eye under perfect conditions. Beyond that, the galaxy extends outward in all directions, an ocean of light too faint to see. The Milky Way's faint band across the sky is the densest part of that ocean, seen edge on from within. Every photon that reaches you from it is the accumulated glow of countless suns. You're not just looking at distant light, you're looking at the structure of your own home from the inside. It's difficult not to feel small when you think about it, but smallness isn't the point. The stars don't diminish you, they include you. The atoms in your body were forged in them, recycled through the galaxy over billions of years. When you gaze at the Milky Way, you're looking at your own history written in light. The connection isn't symbolic, it's physical. You and the stars share the same origin, the same materials, the same cosmic story. The galaxy's stars, scattered like sand, make the Milky Way both vast and familiar. They remind us that scale doesn't erase meaning, it deepens it. From one star comes a solar system, from billions a galaxy, from countless galaxies the universe itself. And through it all, the same process repeats. Hydrogen fusing into helium, light born from gravity, elements created and scattered. The pattern is simple, yet its expression is endless. Out beyond the spiral arms, the density of stars begins to thin. The galactic disk fades into the halo, where ancient stars and globular clusters drift slowly through the dark. Beyond that lies the intergalactic medium, the space between galaxies, thin, cold, and mostly empty. But even there, the light of the Milky Way continues to travel, spreading outward, carrying with it the signature of billions of stars. Eventually, that light will fade into the general glow of the universe, blending with the light of other galaxies until it becomes part of the cosmic background. For now, though, here inside the disk, the stars are close enough to fill the night. Each one is a point in an immense pattern, a tiny piece of the whole. They turn with the galaxy, orbiting the centre in silence, following paths that have been traced for billions of years. The Milky Way moves, and we move with it, drifting among the stars like a single grain among countless others. If you could step far enough away from the Milky Way to see it in full, you'd notice that it doesn't drift through space alone. Around it, smaller galaxies trace wide, slow orbits, like faint satellites circling a great light. Some are bright enough to be visible from Earth with the naked eye, small smudges in the southern sky that ancient peoples noticed long before telescopes existed. Those are the large and small Magellanic Clouds, our closest galactic companions. Together with the Milky Way, they form part of what astronomers call the Galactic neighbourhood, a region of space where gravity binds dozens of galaxies into a quiet cluster moving through the universe together. It's difficult to think of galaxies as neighbours when the distances between them are measured in hundreds of thousands of light years. Yet in cosmic terms, these are close quarters. The Large Magellanic Cloud, or LMC, lies about 160,000 light-years away, and the Small Magellanic Cloud, or SMC, about 200,000. They're irregular in shape, smaller and less organised than the Milky Way's clean spiral. Each is a collection of stars, gas and dust with its own pockets of star formation and clusters. They orbit the Milky Way slowly, shaped and stretched by its gravity, leaving trails of gas that link the three galaxies together. These trails, known as the Magellanic Stream, form a long arc of hydrogen gas that wraps around our galaxy, a reminder of the interactions that bind them. When astronomers study these smaller galaxies, they see the same processes that define our own, but on a reduced scale. The Large Magellanic Cloud, for example, contains the Tarantula Nebula, one of the most active star-forming regions in the local universe. It's a vast complex of gas and dust, where massive stars ignite and die in quick succession. In visible light, it's a glowing tangle of filaments. In infrared, a seething cauldron of new suns. The energy from those stars carves cavities in the surrounding gas, sculpting the nebula into intricate forms. The SMC, though smaller, has its own quiet regions of starbirth, as well as older stars that trace its long irregular history. These companion galaxies are more than just satellites. They're participants in a slow gravitational dance with the Milky Way. Over billions of years, their orbits will decay, and they'll likely merge with our galaxy, adding their stars and gas to its mass. The Milky Way has done this many times before. Around its halo, astronomers have found streams of stars, long, thin trails that curve across the sky. Each stream is the remnant of a smaller galaxy that was captured and torn apart by our own. The stars of those former systems now orbit the galactic centre, indistinguishable from native ones. The Milky Way, like most large galaxies, has grown through such mergers. Its history is written in those faint tidal streams, each one a record of a past collision. If you look beyond the Magellanic Clouds, you come to another neighbour, the Andromeda Galaxy, also known as M31. It's about 2.5 million light-years away, visible to the naked eye as a faint elongated patch in the constellation Andromeda. Unlike the Magellanic Clouds, Andromeda is a giant spiral, similar in shape to the Milky Way but slightly larger. It contains roughly 1 trillion stars, twice as many as our own galaxy. When you see it through a telescope, you're looking across millions of years of distance, seeing light that began its journey long before modern humans existed. Despite that vast separation, the Milky Way and Andromeda are connected by gravity. They're moving toward each other at a speed of about 110 kilometers per second, and in roughly 4 billion years they will collide. The idea of two galaxies colliding sounds catastrophic, but the reality is more gentle than you might expect. Stars are so far apart that few will actually strike one another. Instead, their mutual gravity will distort and merge the galaxy's shapes, flinging long tails of stars into space. Over time, those stars will fall back together, settling into a new, larger, elliptical galaxy. The black holes at each centre will eventually spiral inward and merge, releasing an enormous burst of gravitational waves. From the perspective of any planet within the system, the collision would unfold slowly over millions of years, a gradual change in the night sky as new stars appear and others fade. It's not an end so much as a transformation. Andromeda isn't alone. Between it and the Milky Way lie several smaller galaxies, some irregular, some dwarf spheroidals, each following complex paths through space. Collectively, these systems form what astronomers call the local group, a cluster of more than 50 galaxies bound together by their mutual gravity. The Milky Way and Andromeda are its two largest members, their combined mass dominating the region. Around them orbit the smaller galaxies like moons around planets, each one part of the same gravitational web. The entire group spans about 10 million light-years from edge to edge, though most of its mass is concentrated in the two main spirals and their satellites. The local group moves through the universe as a unit, drifting toward another, larger concentration of galaxies known as the Virgo cluster. Gravity pulls all of these systems toward one another, though the expansion of space itself stretches the distances between them at the same time. It's a delicate balance. Attraction and expansion, motion and distance intertwined. On smaller scales, gravity wins, binding galaxies into groups and clusters. On larger scales, the expansion of the universe dominates, carrying clusters apart. The Milky Way's neighbourhood exists in that balance, held together against the backdrop of an ever-growing cosmos. From our vantage point inside the Milky Way, it's not easy to see this structure directly, Most of the nearby galaxies are faint, and dust in our own galaxy blocks the view towards certain directions. But infrared and radio observations can pierce the obscuring dust, revealing the distribution of galaxies around us. When astronomers map their positions and velocities, the local group takes shape as a three-dimensional network of islands, each one glowing faintly in the dark sea of space. The Milky Way sits on one side of this network, Andromeda on the other, with smaller galaxies like Triangulum, Draco and Sculptor sprinkled between and around them. Each of these galaxies has its own history. Some are ancient, nearly devoid of gas, their star formation long since ended. Others are small but active, with bright regions where new stars are being born. Their shapes vary from irregular clouds to compact ellipses, depending on their mass and the gravitational influence of nearby giants. Many of them are difficult to detect because they emit little light. Some were discovered only in recent years through deep surveys of the sky. These faint companions may hold clues to how galaxies form and evolve. Their interactions with the Milky Way and Andromeda help astronomers understand how larger structures assemble over time. When we talk about the galactic neighbourhood, we're really talking about a hierarchy of scales. The Milky Way and its satellites form one level, the local group another. Beyond that lie clusters and superclusters, vast webs of galaxies stretching across hundreds of millions of light years. Each level is bound by gravity, nested within the next, like ripples expanding outward. Our place within it is both ordinary and remarkable. We live in a typical galaxy, part of a typical group, yet the details of that arrangement have shaped everything about our existence. The position of the Milky Way within the local group determines our motion through space, our future collision with Andromeda, even the way the cosmic microwave background appears in our sky. The Magellanic Clouds, faint though they are, serve as reminders of how connected everything is. They influence the Milky Way structure even now, pulling slightly on its disk and contributing streams of gas that fuel new star formation. When they eventually merge, they'll add fresh material to the galaxy, perhaps triggering a new burst of stellar birth. The Andromeda collision will reshape everything on a larger scale, blending stars and dust into a new form. The galactic neighbourhood is not static. It's a slow-motion dance that will continue long after our sun has faded. Even now, subtle signs of these interactions can be seen. The Milky Way's disk is slightly warped, likely due to the gravitational tug of the Magellanic Clouds or other nearby dwarfs. Streams of stars arc through the halo, remnants of galaxies that once orbited here. The shape of the Milky Way's dark matter halo, inferred from the motion of distant stars, suggests that it too has been sculpted by past encounters. Every small galaxy that approaches leaves an imprint, a faint echo of its passage written into the orbits of stars. If you could watch the neighbourhood unfold over billions of years, you'd see galaxies approach and recede like ships on a vast ocean. Some would drift together and merge, others would pass without touching. The light from each would mix with the others, their stars blending until individual origins were lost. The Milky Way as we know it is only a momentary shape in that long evolution. Its spiral arms, its satellites, its quiet companion galaxies, all are temporary configurations in an ongoing process of motion. From our small world near the edge of the Milky Way, it's easy to forget how interconnected these systems are. The light from the Magellanic Clouds reaches us after hundreds of thousands of years, the light from Andromeda after millions. Yet the gravity that binds us all acts instantly across those scales, tying the neighbourhood together into one vast invisible structure. When you step outside and look at the sky, you're not just seeing the stars of our galaxy. You're seeing the faint hints of a community of galaxies, each shining across the same space, each part of the same cosmic neighbourhood. And beyond that neighbourhood lies something even larger. The local group itself belongs to a greater web, a vast cluster of galaxies called Laniakea, a supercluster so large that even light would take hundreds of millions of years to cross it. The Milky Way is only one of its countless members, drifting along gravitational currents that stretch across unimaginable distances. From the scale of our galaxy, it's difficult to imagine such vast structures, but the same principles that hold the Milky Way together also hold Laniakea together. Gravity binds everything, from the smallest cluster of stars to the largest pattern in the cosmos. The Milky Way, though vast beyond imagining, is not alone in its drifting. When we step back from our galaxy and trace its place among others, we find ourselves in a small gravitational family, one that moves quietly through space, bound not by walls or borders, but by gravity's unbreakable thread. This family is called the Local Group, a gathering of more than 50 galaxies, each one turning, colliding and evolving in its own way, yet all sharing a common gravitational fate. To picture it, imagine standing somewhere far beyond the galaxies, in a space so wide that you could see them all suspended before you. The Milky Way would appear as a spiral disk of light, pale and graceful, roughly 100,000 light-years wide. Nearby, a similar spiral, Andromeda, would float in the dark, slightly larger and brighter. Between them and around them would shimmer dozens of faint smudges, the smaller galaxies that orbit these two giants. They're irregular in shape, diffuse and dim, but together they complete the Local Group structure. It's a collection of islands adrift in the same cosmic current, each influencing the others through invisible strands of gravity. The Milky Way and Andromeda dominate this small domain. Their combined mass accounts for nearly all the gravitational binding energy of the group, shaping the orbits of every smaller companion. The third largest member, the Tranquil Galaxy, or M33, lies near Andromeda, about 3 million light-years from us. It's a smaller spiral, roughly half the Milky Way's size, full of active star-forming regions. Some evidence suggests that Tranquil may be a satellite of Andromeda, orbiting it slowly, though their relationship is still uncertain. Beyond these three main spirals, the rest of the Local Group is made up of dwarf galaxies, some no larger than star clusters, some so faint that they've only recently been detected through deep surveys. These dwarfs come in many forms. Some, like the Magellanic Clouds, still contain gas and form new stars. Others are ancient and quiescent, their gas long gone, their stars old and red. Many of them orbit the Milky Way or Andromeda in elongated paths, looping through space like moths drawn to light. Over time, their orbits decay, and they're pulled apart by tidal forces. When that happens, their stars spread into thin streams that wrap around the larger galaxy, contributing to its halo. The Milky Way's outer regions are full of such remnants, faint rivers of stars marking the ghosts of galaxies long absorbed. To understand how these systems move together, astronomers map their positions and velocities using precise observations from space telescopes like Gaia and Hubble. When plotted in 3 dimensions, the Local Group reveals itself as a loose cluster spanning roughly 10 million light-years across. The Milky Way and Andromeda sit near the centre, separated by about 2.5 million light-years and slowly drawing closer. Around them, smaller galaxies scatter in all directions like sparks from a fire. Despite that appearance, their motions are coordinated. They orbit a shared centre of mass, a point that lies somewhere between the Milky Way and Andromeda, invisible yet decisive. It's the gravitational balance point that keeps the group bound together. Gravity, however, doesn't hold everything perfectly still. The Local Group is not a static arrangement, but a dynamic one. Every galaxy moves relative to the others, tracing long, graceful trajectories through the void. The Milky Way and Andromeda are on a collision course, moving toward each other at roughly 110 kilometers per second. Their meeting will take place about 4 billion years from now. When it happens, their disks will begin to merge, their stars passing harmlessly through one another, while their gas clouds collide, igniting bursts of new star formation. The final result will be a single larger galaxy, perhaps elliptical in shape, its 2 central black holes spiraling together until they merge. Astronomers sometimes call this future system Milkomeda, a poetic name for what will remain of both galaxies after the collision. Even now, the influence of that future is visible. The Milky Way's outer disk is slightly warped, likely due to the gravitational tug of Andromeda and other members of the group. The same pull shapes the motion of nearby dwarf galaxies, drawing them into complex orbits that evolve over time. When astronomers measure the motion of the local group as a whole, they find that it's not at rest relative to the larger universe. It's moving toward a region of higher density, drawn along by the combined gravity of distant clusters. This motion, known as the local group's peculiar velocity, is part of a grander flow that connects us to the cosmic web at large. Between the galaxies of the local group lies intergalactic space, a region not empty, but filled with a thin haze of gas and dark matter. This medium acts as a bridge, a continuous field that links all members of the group. When galaxies pass close to one another, they exchange material through tidal forces, pulling gas and stars across the vastness. The Magellanic Stream, stretching behind the Milky Way's companion galaxies, is one such bridge, a river of hydrogen gas connecting galaxies across hundreds of thousands of light years. These interactions feed star formation, recycle matter, and shape the evolution of each system involved. The local group's composition also reveals clues about how galaxies form and evolve. The presence of so many dwarf galaxies suggests that they're the building blocks of larger ones. In the early universe, small clumps of matter merged under gravity to form progressively larger systems. Some dwarfs were absorbed into spirals like the Milky Way, while others survived as satellites. Even today, the process continues on a smaller scale. The Sagittarius dwarf galaxy, currently merging with the Milky Way, leaves a trail of stars across our sky, a visible reminder that galaxy formation is an ongoing story. Most of the mass in the local group isn't in stars or gas, it's in dark matter, the unseen substance that makes up most of the universe's mass. Though we can't detect it directly, its presence is inferred from the motion of galaxies. The entire group is embedded within a vast dark matter halo, an invisible structure that provides the gravitational glue holding everything together. Without it, the galaxies would drift apart under the expansion of the universe. The scale of this halo is staggering, hundreds of times wider than the visible region, stretching millions of light years into space. It's a reminder that what we see is only a fraction of what exists. When astronomers study the local group, they're also studying cosmic history, the distribution of its galaxies, their velocities and their chemical compositions all carry information about how the universe evolved. Some galaxies are rich in heavy elements, meaning their stars have lived and died many times. Others are pristine, made almost entirely of hydrogen and helium from the Big Bang. Together they form a kind of timeline, a record of how matter condensed into stars and galaxies over billions of years. By comparing the local group to other galaxy clusters, scientists can test theories about cosmic evolution and the role of dark matter in shaping structure on every scale. From Earth, only a few of these galaxies are visible without instruments, but they're there, surrounding us in all directions. Through a telescope, the Andromeda galaxy is a pale oval with a bright core, its light the sum of 1 trillion suns. The Magellanic clouds are smaller, but close enough that individual stars and nebulae can be resolved. The dwarf galaxies are too faint for the eye, their stars scattered thinly across large areas of sky. Yet each one, no matter how dim, contributes to the gravity that binds the group. Together, they create a network of orbits and interactions, a delicate structure balanced across space. To think of the local group is to think of motion on an unimaginable scale. Every galaxy within it is in motion, rotating, orbiting, colliding. The distances are so vast that we perceive no change, but over millions of years everything shifts. The Milky Way itself moves at over 200 kilometers per second around the group's center of mass, while the entire group drifts through the universe at hundreds of kilometers per second relative to the cosmic microwave background. Even standing still, we're carried along by these currents, part of a vast and unending flow. Within that flow, the boundaries between galaxies blur. Streams of gas connect them. Dark matter halos overlap, and gravity weaves everything together. The local group is a microcosm of the universe, a small-scale version of the larger cosmic web. It contains diversity, interaction, and constant change. It shows that galaxies are not isolated entities, but participants in a larger dynamic structure. And though we can name them, measure them, and map them, their story is still unfolding. If we could fast-forward through time, the picture would transform. The Milky Way and Andromeda would draw closer, their disks stretching and twisting as they approach. The dwarf galaxies would shift their paths, some captured by the growing giant, others flung into intergalactic space. After the merger, the new galaxy would shine brighter but smoother, its spiral arms gone, its shape more rounded. The smaller galaxies would continue to orbit it, their own shapes distorted by its gravity. Eventually, the local group itself might merge with nearby clusters, forming an even larger structure. Nothing in the universe remains fixed. Even clusters evolve, merging into ever larger systems as time unfolds. From our current moment, though, the local group appears calm. Its galaxies move on paths so long that we can only trace a fraction of their journey. The stars within them burn quietly, their light bridging millions of years of distance. The space between them, though nearly empty, hums with potential. The subtle pull of gravity, the faint glow of scattered gas, the slow drift of matter toward new configurations. To observe this neighbourhood is to glimpse a living system, one that connects our small corner of the Milky Way to the immense structures beyond. When you step even farther back from the local group, so far that the Milky Way and Andromeda appear as two tiny smudges of light lost in a faint mist, the pattern of the universe begins to change. You no longer see individual galaxies, but the larger structures they form. Clusters, filaments, and vast empty voids that stretch across unimaginable distances. On this scale, the universe resembles a web, an intricate network where matter is not spread evenly, but gathered into enormous threads that wind around empty spaces. Within one of those filaments lies our home region, a sprawling complex of galaxies bound together not just by gravity, but by the flow of space itself. Astronomers call this region the Laniakea supercluster, a word from Hawaiian meaning immense heaven. It is a fitting name, both poetic and literal, for the structure that contains our galaxy. Laniakea is vast on a scale that defies intuition. It spans more than 500 million light-years and contains an estimated 100,000 galaxies, each one a Milky Way or an Andromeda in its own right, each filled with billions of stars. To cross it at the speed of light would take 500 million years, longer than the history of multicellular life on Earth. Yet even this enormity is not a separate island in the universe. It's part of a larger cosmic web, connected to neighbouring superclusters through bridges of galaxies and filaments of dark matter. The boundaries between them are not walls, but gentle transitions where the flow of galaxies changes direction, like the divides between river basins. Understanding that flow is how astronomers defined Laniakea in the first place. For most of the 20th century, scientists knew that galaxies were not scattered randomly, but grouped into clusters and superclusters. However, the scale and shape of these structures were uncertain. That changed in 2014, when a team of researchers mapped the motions of thousands of galaxies and noticed something remarkable. The galaxies in our region weren't drifting aimlessly. Their movements formed coherent patterns, as though they were being pulled towards certain regions and away from others. By tracing those motions backward, the scientists could identify the gravitational centers guiding the flow. The result was a map showing that our local group, the Virgo cluster, and several other nearby clusters were all part of one enormous structure, Laniakea. Within this supercluster, gravity and cosmic expansion coexist in a delicate balance. The universe is expanding overall, but within regions like Laniakea, the mutual attraction of matter overcomes that expansion, keeping galaxies loosely bound together. They don't collapse into a single mass, but they move within the same gravitational basin, flowing like water toward a common centre. That centre is known as the Great Attractor, a region about 250 million light-years away, where the combined gravity of countless galaxies draws everything nearby toward it. The Milky Way, Andromeda, and the rest of the local group are all falling slowly in that direction, moving at hundreds of kilometers per second relative to the cosmic background. We can't see the Great Attractor directly because it lies behind the dense plane of our own galaxy, hidden by gas and dust, but its influence is unmistakable. The idea that our entire galaxy and all its neighbours are part of a gravitational current moving toward a hidden mass is both humbling and strangely comforting. It means that even on the larger scales, the universe has structure, rhythm and direction. Every galaxy we can see belongs to some flow, drifting toward or away from other concentrations of matter. The cosmos is not static. It's a vast system of motion, with currents that stretch across hundreds of millions of light-years. Laniakea is one of those currents, a basin in the cosmic landscape where gravity collects galaxies like rainwater, gathering in a valley. When we talk about size on this scale, numbers start to lose meaning. A single light-year is nearly 10 trillion kilometers. 1 million light-years separates our galaxy from Andromeda. 100 million light-years is the distance between the Milky Way and the nearest large clusters of galaxies, and Laniakea stretches 5 times farther still. Even the concept of distance becomes slippery because the fabric of space itself is expanding. The farther away something is, the faster it recedes from us, not because it's moving through space, but because space itself is stretching. The galaxies within Laniakea are bound together against that expansion, but beyond its edges the flow of space takes over, carrying other superclusters away from us faster than light can cross the gap. The supercluster is not a single object, but a region defined by motion. Within it are several major components, including the Virgo cluster, which lies about 65 million light-years from us, and contains more than 1,000 galaxies. The Milky Way sits on the outskirts of this cluster, connected by filaments of galaxies that act like highways through the void. One of these filaments links us to the Centaurus cluster, another massive congregation of galaxies near the Great Attractor. The paths between clusters are lined with smaller groups, each connected to the next by thin chains of galaxies and gas. From a distance, it would look like a network of glowing strands, luminous where galaxies cluster and dark in between. This web-like structure is one of the most striking features of the universe. Computer simulations of cosmic evolution show how it formed. After the Big Bang, matter was nearly uniform, with only slight variations in density. Over billions of years, gravity amplified those tiny differences, pulling matter into filaments and leaving behind empty regions called voids. Galaxies formed along those filaments where the density was highest, and clusters developed at their intersections. Laniakea is one of those intersections, a massive node in the cosmic web, shaped by billions of years of gravitational evolution. From our perspective inside it, Laniakea is invisible to the eye. We can't look out and see its shape directly. We infer it from measurements of galaxy positions and velocities, from maps that show how the light of distant galaxies is redshifted by their motion, and from the gravitational lensing of light as it passes through massive clusters. When astronomers render it in 3 dimensions, the result is astonishing. A cloud-like formation with filaments stretching out in all directions, connecting clusters like beads on threads. The Milky Way sits near one edge, not at the centre, but part of the same flow that leads inward toward the Great Attractor. Even within this immense structure, the balance between gravity and expansion is temporary. Over the next tens of billions of years, the expansion of the universe will continue to accelerate, driven by dark energy. Eventually, galaxies beyond our local region will drift so far away that their light will no longer reach us. The Laniakea supercluster, once connected to its neighbours, will become increasingly isolated. In the far future, only the galaxies within our gravitational basin will remain visible, the rest receding beyond the cosmic horizon. The universe will appear smaller again, though it will not have changed. Only our ability to see it will have diminished. When you think about this scale, it's easy to feel detached, as if the universe's immensity makes human life trivial. But the opposite can also be true. The same forces that shaped Laniakea, gravity, motion, time, shaped everything, down to the atoms in your body. The matter that forms you was once part of the same flow, drawn along the same cosmic filaments. You exist within this supercluster, not as an observer outside of it, but as a participant, part of its mass, moving with it through space. The atoms in your bones are as old as the structures that define the cosmos. From Earth, the evidence of this supercluster is subtle. The galaxies visible in our telescopes appear scattered randomly, but when plotted together they reveal the hidden order. The Virgo cluster shines as a dense knot of light. Beyond it, the Hydra and Centaurus clusters form another region of brightness. Between them lies the zone of avoidance, where the dust of the Milky Way blocks our view, yet even there, radio telescopes can detect the faint signatures of galaxies. These observations stitch together a picture of an enormous, interconnected structure. Our home supercluster, immense and still growing as gravity continues to draw matter inward. The name Laniakea is more than just poetic. It reflects our relationship with what we see. When the scientists who defined it chose that name, they were acknowledging both the scale of the discovery and the humility it inspires. To call it immense heaven is to recognize that we are surrounded by something too vast for measurement to truly convey, something that invites wonder rather than certainty. Science can map it, calculate its mass, and trace its motion, but there's a part of its meaning that can only be felt, the sense of belonging to something larger than comprehension. If you could look across Laniakea from one side to the other, the Milky Way would be invisible, a faint dot among thousands. Even Andromeda, the giant next door, would be lost in the brightness of the whole. Clusters would appear as tiny knots of light, connected by thin strands glowing faintly with the collective shine of galaxies. Between those threads would lie darkness, the great cosmic voids, regions almost empty, where galaxies are scarce and light is rare. The contrast between fullness and emptiness is part of what defines the structure. The universe, when seen on this scale, is mostly void, but the small fraction that contains matter forms patterns of breathtaking beauty. Through telescopes and data, through patient observation and imagination, we can trace our place in this vast pattern, from the heart of the Milky Way to the local group, from the local group to the Virgo cluster, and from there to the full sweep of Laniakea. Each level of structure leads to another, larger one. It's like zooming out from a single leaf to the forest, from the forest to the continent, and finally to the planet itself. The scale changes, but the principle remains. Everything is connected, everything follows the same laws, and beyond even Laniakea, there are more superclusters, Perseus Pisces, Coma, Shapley and others, each a vast congregation of galaxies, each part of the same cosmic web. There's no center to it, no edge, no boundary where the universe ends, only more structure, more light, and more darkness in between. The Milky Way is one small participant in that grand design, drifting through its lane in the great river of the cosmos. If you step outside on a clear night and let your eyes adjust, the light you see above you is part of that river. Every star, every faint galaxy visible in the telescope's field belongs to this immense system. The light may seem fragile, scattered, insignificant, but together it traces the architecture of everything that exists. The Milky Way is only one curve in that vast network, a single swirl in the great motion of Laniakea, and through it all we drift quietly, carried along with every other galaxy toward the unseen depths of space. When astronomers began mapping the positions of galaxies across the sky, they expected to see a kind of uniform scatter, a random distribution of light marking an even spread of matter through the universe. Instead, what emerged was a pattern so intricate and vast that it seemed almost alive. Galaxies were not scattered like dust. They were arranged in filaments, clusters, and great sheets, with enormous empty spaces between them. These structures stretched across hundreds of millions of light years, forming a connected network that spanned the entire observable universe. The pattern became known as the cosmic web, and it remains one of the most profound and beautiful discoveries in modern cosmology, a map of how the universe organizes itself on the grandest possible scale. From the perspective of an observer on Earth, the night sky appears flat, a sphere of stars and galaxies scattered across a dome. But when we measure the distances to those galaxies and plot them in 3 dimensions, a very different picture appears. The galaxies line up in long filaments that weave around vast empty regions called voids. These filaments intersect at nodes, dense regions where clusters and superclusters of galaxies form. The result looks like a giant 3-dimensional web, with luminous threads stretching across the darkness. Each filament can be hundreds of millions of light years long and millions of light years thick, containing thousands of galaxies bound together by gravity and the invisible scaffolding of dark matter. The discovery of this structure began in the late 20th century, when large-scale galaxy surveys became possible. By measuring the redshift of each galaxy, a shift in its light caused by the expansion of the universe, astronomers could determine its distance. When they plotted thousands, then millions of galaxies, the cosmic web emerged naturally from the data. It wasn't an illusion or a coincidence, it was the true shape of the universe on the largest scales. Clusters of galaxies connected into filaments, and between them lay enormous voids spanning hundreds of millions of light years, regions almost completely empty of galaxies. The scale of these structures dwarfs anything else we can imagine. The cosmic web isn't just a pattern of galaxies, it's the architecture of matter itself. It traces the distribution of both visible and invisible mass, stars, gas, dark matter, shaped by gravity over billions of years. In the early universe, matter was nearly uniform, a smooth soup of hydrogen and helium with tiny fluctuations in density. Those fluctuations, amplified by gravity, became the seeds of structure. Regions slightly denser than average pulled in more matter, growing denser still while less dense regions lost matter and became voids. Over time, this process formed a vast network of overdense filaments and underdense voids. The light we see today, from galaxies and clusters, is just the bright frosting on that invisible structure. The web itself is mostly dark matter, unseen but measurable through its gravitational influence. To understand how the cosmic web formed, scientists use massive computer simulations, starting from conditions just after the Big Bang. They input the physics of gravity, cosmic expansion, dark matter and dark energy, then let the simulation evolve over billions of years. The result is always the same, a universe filled with filamentary networks that match the observations almost exactly. Galaxies form where filaments intersect, and gas flows along those filaments toward the nodes, feeding new star formation. The web is not static, it's dynamic, with matter continually moving along its strands. Galaxies migrate through it like plankton drifting in ocean currents, carried by the invisible pull of gravity. If you could see the cosmic web directly, it would resemble a vast glowing network suspended in darkness, with luminous filaments connecting bright knots of light. The voids between them would appear almost black, though even there, a faint haze of gas and dark matter would remain. The entire structure is interconnected, stretching across the observable universe like the threads of a cosmic fabric. There is no true edge, only gradual thinning, as the density of galaxies decreases at greater distances. Every galaxy, including our own, lies somewhere within this network, on a filament, near a junction, or along a bridge connecting larger clusters. The Laniakea supercluster, which contains the Milky Way, is one of many nodes in this web. Beyond it, other superclusters, like Perseus Pisces and Shapley, lie along neighbouring filaments. These filaments connect to one another, forming a continuous structure that spans billions of light years. The empty spaces between them, the cosmic voids, are among the largest known features in the universe. Some of them are hundreds of millions of light years wide, vast bubbles of near-total emptiness where only a few galaxies reside. In a sense, the cosmic web is defined as much by these voids as by the filaments that surround them. It's the contrast between fullness and emptiness that gives the universe its structure. Despite its complexity, the web follows simple physical principles. Gravity pulls matter together, while cosmic expansion pushes it apart. The balance between these two forces shapes everything we see. Where matter is dense, gravity dominates, forming clusters and filaments. Where it's sparse, expansion wins, creating the voids. Dark matter plays a central role in this process. Though it neither emits nor absorbs light, it makes up about 85% of the universe's total matter. It forms the framework of the web, providing the gravitational wells where normal matter collects. Galaxies form within those wells, lighting up the dark scaffolding like dewdrops along a spider's thread. The cosmic web also carries the imprint of the universe's earliest moments. The pattern of its filaments and voids reflects the distribution of matter in the first few 100,000 years after the Big Bang, as seen in the cosmic microwave background radiation. Tiny ripples in that ancient light correspond to the seeds of today's large-scale structures. In a way, the cosmic web is the grown-up version of those primordial fluctuations, a vast, three-dimensional fossil of the universe's beginnings, stretched and evolved over nearly 14 billion years. From Earth, we can't see the cosmic web with our eyes, but we can detect its presence in subtle ways. When light from distant galaxies passes through the intergalactic medium, the thin gas that fills the space between galaxies, it's absorbed at specific wavelengths, leaving characteristic fingerprints in the spectrum. These absorption lines reveal the distribution of hydrogen along the line of sight, effectively tracing the web's filaments. Astronomers also study the web through gravitational lensing, the bending of light by mass. The gravity of dark matter in the filaments distorts the light of more distant galaxies, allowing scientists to map the invisible structure indirectly. Piece by piece, observation and theory combine to form a coherent picture. The universe is a web, and every galaxy is part of it. The scale of the cosmic web challenges our sense of perspective. The Milky Way, so enormous compared to human experience, becomes a point of light along one of its filaments. The local group is a small cluster within that point. Laniakea is one of many nodes in the web, and beyond the web's visible extent, space continues, perhaps infinitely, perhaps looping back on itself in ways we can't yet perceive. The farther we look, the more the boundaries of comprehension stretch. Yet the pattern remains consistent. Clusters, filaments, and voids repeating across the universe like a cosmic rhythm. In recent years, astronomers have begun to detect the faint glow of gas within the filaments themselves, confirming that they are not empty bridges but rivers of matter connecting galaxies. These rivers carry hot, diffuse plasma, the raw material for new galaxies and stars. They also guide the motion of existing galaxies, funneling them toward denser regions. The entire universe, on every scale, seems to follow this same principle. Matter flowing along gradients, gathering into structures, radiating energy, and then dispersing again. The cosmic web is both the skeleton and the circulatory system of the cosmos. If you could travel across it, the journey would be beyond imagination. Between one filament and another lies a void so vast that, if you could cross it at the speed of light, it would still take hundreds of millions of years to reach the next structure. Inside the filaments, galaxies cluster together like glowing embers in a fire. their light forming a thin, luminous mist. Every direction would look similar, endless networks of brightness surrounded by the deep dark of space. The closer you look, the more structure you'd see. Galaxies within clusters, clusters within filaments, filaments branching into smaller threads, down to the scale of individual galaxies and their internal webs of stars and gas. The same pattern repeats, from the largest structures in the universe to the smallest ones we can observe. This repetition is one of the most striking aspects of nature. The universe builds itself through self-similarity. The shapes of spiral galaxies resemble the arms of hurricanes. The filaments of the cosmic web echo the networks of neurons in a brain. These are not exact parallels, but they reveal a common theme. Systems organize themselves through simple rules that generate complexity. Gravity, motion, and time are the rules of the cosmos, and from them arises the web of everything. Our place within this web is modest but not meaningless. The Milky Way's position along a filament connects us to everything else. The same gravitational flows that guide entire clusters also guide our galaxy's motion. When we look at the sky, we're seeing light that traces those connections. Each point of light is a node in the network, a reminder that we're part of a structure far larger than ourselves. The atoms in our bodies, the stars in our sky, and the galaxies in our telescope images all share the same cosmic heritage. It's difficult to comprehend a structure that spans billions of light years, but the fact that we can describe it at all is extraordinary. From a small planet orbiting a single star, we've managed to reconstruct the universe's largest pattern. The cosmic web isn't just a map of matter, it's a map of understanding. It shows how far human curiosity has reached and how much more remains to explore. Every filament we chart, every void we measure, adds to that growing picture, a picture of a universe that is both immense and connected, governed by simple forces yet capable of infinite complexity. When you look up at the night sky, what you see is not a picture of the universe as it is now. It's a collection of moments stretched across time, a mosaic assembled from light that has taken millions or even billions of years to reach you. Every photon carries a timestamp, a record of when it began its journey. Some of those photons left nearby stars only years ago. Others began travelling when dinosaurs still walked the Earth. The farther we look, the deeper we peer into the past. There's a limit to how far that gaze can reach, a boundary set not by the size of the universe itself, but by the time light has had to travel since the beginning of everything. That boundary is called the cosmic horizon. The cosmic horizon defines the edge of the observable universe. It's not an edge in the physical sense. There's no wall, no barrier, no point where space ends. It's a limit of visibility. Beyond it, light has not had enough time to reach us since the universe began. The age of the universe is about 13.8 billion years, but because space has been expanding the entire time, the most distant regions we can observe are now about 46 billion light-years away. This means the observable universe is a sphere centered on every observer, about 93 billion light-years across. Everything inside that sphere is connected to us by light. Everything beyond it lies outside our ability to see, not because it doesn't exist, but because its light hasn't arrived yet, and perhaps never will. The horizon isn't static. It changes with time. As the universe ages, light from more distant regions has time to reach us, expanding the boundary of what's observable. But at the same time, cosmic expansion stretches space faster and faster, carrying distant galaxies away. In the early universe, gravity and expansion were more evenly matched. Over time, however, a mysterious force known as dark energy began to dominate, accelerating the expansion. The result is that some galaxies are now receding faster than the speed of light, not because they're moving through space that quickly, but because the space between us and them is stretching. Light from those galaxies will never reach us. They're already beyond our future light cone, effectively disappearing from our cosmic horizon. When astronomers observe the most distant galaxies, They're seeing them not as they are now, but as they were billions of years ago, often when the universe was only a fraction of its current age. These galaxies appear small and faint. Their light shifted toward the red end of the spectrum, an effect known as redshift. The redshift occurs because as the light travels through expanding space, its wavelength stretches, lowering its energy. The greater the redshift, the farther away the galaxy, and the older the light we're seeing. At the highest redshifts, we approach the very edge of visibility, the point where the first galaxies formed out of the cooling cosmic gas. Beyond that lies the afterglow of the Big Bang itself, the cosmic microwave background. That background is the ultimate horizon, the oldest light we can detect. It was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely through space. Before that time, the universe was opaque, a hot, dense plasma where photons bounced endlessly off electrons and protons. When that fog lifted, light was released in all directions, filling space with a uniform glow. Over billions of years, that radiation stretched into microwaves as the universe expanded. Today, it surrounds us as a faint, nearly uniform background of energy, detectable in every direction. It's the most distant thing we can see, the cosmic horizon's inner wall, marking the transition from the universe's opaque youth to its transparent maturity. When scientists first detected the cosmic microwave background in 1965, it confirmed the Big Bang theory and provided a snapshot of the early universe. Tiny fluctuations in its temperature, differences of only a few millionths of a degree, revealed the seeds of structure that would later grow into galaxies and clusters. Those ripples are the foundation of everything we see today, the first hints of the cosmic web. The background isn't just the edge of our view, it's the beginning of our story. But what lies beyond that horizon remains unknown. The universe may extend infinitely beyond what we can see, or it may curve back on itself, forming a kind of cosmic loop. The observable universe is like a bubble within a much larger sea of space-time. We can only measure what light has had time to reach us, but physics suggests that the cosmos continues far beyond those limits. In that unseen region, galaxies may exist that will never be visible from Earth, forever out of reach due to the accelerating expansion of space. If you could stand in one of those galaxies and look outward, your own observable universe would form a different sphere, overlapping ours in some regions but not in others. Every observer, wherever they are, stands at the centre of their own cosmic horizon. That symmetry is one of the most beautiful truths of cosmology. There is no privileged vantage point. Every place in the universe, no matter how distant, has its own horizon defined by the same rules of light and time. From any galaxy, the universe looks roughly the same on large scales, filled with the same cosmic web, the same background radiation, the same endless expansion. The universe has no true centre. The cosmic horizon doesn't mark a boundary of where the universe ends. It marks the limit of where each observer's story of light begins. Understanding this horizon means understanding that seeing is always looking backward. The farther we look, the further into time we reach, until the horizon becomes the earliest possible moment we can observe. It's not just a boundary in space, but in history. Each telescope we build extends our reach slightly farther, pushing the frontier of sight closer to that origin. The James Webb Space Telescope, with its infrared eyes, can see light from galaxies formed less than 300 million years after the Big Bang. Beyond those galaxies lies only darkness, not empty space, but a time before light could travel freely. Cosmic horizons also exist in other forms. Around black holes, for example, an event horizon marks the boundary beyond which light cannot escape. In a sense, the universe's cosmic horizon is a larger version of the same concept. It defines the region from which information can reach us. Beyond it, events occur, but we will never know of them. That limit is not imposed by any physical barrier, but by the speed of light and the expansion of space. the fundamental properties of the universe itself. The existence of this horizon has profound implications for how we think about the universe. It means that much of what exists is forever hidden from us, not because we lack the tools to see it, but because it lies beyond the reach of causality. The universe we can observe is only a small fraction of the whole. When cosmologists describe the cosmos, they speak carefully, not of the universe as a whole, but of the observable universe. Beyond that, all is speculation. Yet even within that limitation, we've managed to uncover extraordinary detail about how the universe works, how it grew from the smooth glow of the microwave background into the complex cosmic web we see today. For those who study it, the horizon is not a frustration, but an invitation. It's the edge of what can be known, the boundary that science constantly pushes against. Each improvement in technology extends it a little farther, adding faint new galaxies to our maps. Every photon captured from the edge of the observable universe is a message from the past, carrying information across billions of years. The light from the most distant galaxy known left its source when the universe was less than 5% of its current age. To detect it now is to bridge that immense gulf of time and space, to connect the beginning with the present in a single line of sight. If you could stand outside the Milky Way and look across the observable universe, you would see billions of galaxies arranged in filaments and clusters, fading gradually into the dim red of the most distant regions. Beyond that, you'd see the afterglow of the Big Bang itself, the cosmic microwave background, uniform and ancient. And beyond that, nothing. Not because nothing exists, but because no light from there has reached you yet. It's a darkness filled with potential, a frontier that recedes as fast as we can approach it. Cosmic horizons remind us that knowledge always has limits. They show that even in a universe governed by the laws of physics, there are boundaries we cannot cross. Yet those boundaries are what give shape to understanding. They define what can be known, and in doing so, they make the act of knowing meaningful. The universe doesn't hide itself maliciously. It simply obeys its own rules. Within those rules, light moves at its steady speed, space stretches, and time carries everything forward. The horizon is where those rules meet perception, and even though it marks the edge of what we can see, it's not the end of wonder. Beyond the cosmic horizon, the universe continues, full of galaxies and structures we'll never witness. Their light is still on its way, some of it perhaps destined never to arrive. The cosmos is vast enough that every observer sees only a fragment, but within that fragment lies the entire history of everything that has ever been visible. When you look into the night sky, you're seeing not only distance but time itself, a window into the past bounded by a horizon that keeps moving outward as the universe grows older. What lies beyond the edge of everything we can see? It's one of those questions that seems simple when you first ask it, yet the more you think about it, the more it stretches into something enormous. The observable universe, that glowing sphere defined by light's long journey since the Big Bang, is not the whole of existence. It's just the portion that has had time to reveal itself. Beyond that limit, space doesn't stop. It keeps going, expanding, continuing the same patterns we can already see, or perhaps diverging into something stranger, something we can only imagine. When we talk about what's beyond the observable universe, we enter a realm where direct evidence ends and inference begins. No light, no radiation, no signal of any kind can reach us from those regions. They are causally disconnected from our own, separated not by walls but by time itself. Yet physics tells us they must exist, because the universe doesn't seem to have a boundary. The simplest models of cosmology describe space as continuous, without edge or center. That means the observable universe is like a small patch on an infinite fabric, the part illuminated by our light cone, surrounded by vast regions that remain dark to us simply because their light hasn't had time to arrive. If you could step outside our horizon and look around, you would not find an edge marking where the universe ends. you would simply find more space, more galaxies, more of the same. Somewhere out there, beyond our line of sight, the pattern continues. Clusters and filaments of galaxies stretching in every direction, the cosmic web unbroken. Every observer, wherever they are, has their own observable universe centered on themselves, each one overlapping slightly with others, like ripples in a vast pond. From their perspective, we would be part of the unseen beyond, a galaxy too distant, too faint, our light not yet reaching them. This idea that the universe continues indefinitely beyond what we can see is supported by observations of its shape. Measurements of the cosmic microwave background, the oldest light in the universe, show that space is remarkably flat on large scales. In general relativity, that flatness means the universe could extend infinitely, or at least much farther than the portion we can observe. If space were curved like the surface of a sphere, we might eventually see evidence of that curvature, perhaps repeated patterns in the microwave background where light has circled the cosmos. But so far, no such repetitions have appeared. To the best of our measurements, the universe is either infinite or so large that its curvature is imperceptible within our horizon. Infinity is a hard concept to hold. We live in a world of boundaries. Oceans have shores, mountains have peaks, lifetimes have limits. The idea of a universe without end is something the human mind can describe mathematically but never truly picture. Yet that's what the evidence suggests. Beyond the farthest galaxies, beyond the reach of any possible light, the cosmos may stretch forever. Every direction leads to more space, more stars, more galaxies, a continuation of the same grand structure, repeated endlessly. Still, infinity isn't the only possibility. Some cosmological models suggest that the universe could be finite but unbounded, like the surface of a sphere in higher dimensions. You can travel around the surface of the Earth indefinitely without ever finding an edge, even though the planet itself is finite. The universe could be similar, curved back on itself so subtly that, on the larger scales, travelling far enough in one direction might eventually bring you back to your starting point, though the distance required would be unimaginably vast, far beyond the limits of observation. There's also the question of variation. Even if space extends indefinitely, the parts we can't see might not look exactly like the part we inhabit. The laws of physics, as we understand them, may be universal, but the specific conditions, the arrangement of galaxies, the density of matter, the local values of certain physical constants might differ. In some regions, galaxies might be more densely packed, in others, sparser. Some areas might have experienced slightly different rates of expansion, resulting in cosmic patches that evolve differently over time. Beyond the observable universe, the universe might still follow the same rules but play out endless variations of structure and form. This idea leads naturally to another, the multiverse. It's a word that often appears in popular science and fiction alike, but in cosmology, it refers to specific possibilities suggested by physics. One version arises from cosmic inflation, the theory that describes how the universe expanded exponentially in the first fraction of a second after the Big Bang. According to this theory, inflation didn't necessarily end everywhere at once. Instead, it may have continued in different regions, creating countless separate bubble universes, each with its own space, time, and physical properties. Our observable universe would then be just one bubble in an endless cosmic foam, isolated from the others by space still expanding faster than light. If that's true, there could be regions of the cosmos with different physical constants, places where gravity is weaker or stronger, where atoms form differently, where stars burn in unfamiliar ways. Some bubbles might be sterile, unable to form complex matter. Others might be too chaotic for stable galaxies to exist. Ours might simply be one where the conditions happen to allow complexity, and therefore consciousness, to emerge. In that view, the vastness beyond our horizon isn't just more of the same. It's a landscape of universes, each one with its own version of reality. There's no way to confirm or refute this yet. The other universes, if they exist, would be permanently cut off from us by the accelerating expansion of space. No signal could ever cross the gap. They are beyond not only our observable horizon, but beyond any possible horizon. And yet the mathematics of inflation and the distribution of galaxies we see make the idea plausible. The structure of the cosmos seems to hint at processes larger than any single universe. Whether or not those other regions are truly separate universes or simply distant parts of one infinite whole, they remind us how limited our perspective really is. Even within our own cosmic bubble, the universe beyond the observable continues to influence what we can see. The gravitational pull of matter outside our horizon subtly affects the motion of galaxies within it, shaping the flow of large-scale structures. These unseen regions exert real influence, even though their light will never reach us. In that sense, the universe we observe is incomplete but not isolated. It's part of a larger system that extends beyond measurement. When you think about this scale, horizons within horizons, expanding space, possible infinities, it becomes clear that observation is only one kind of knowing. We can model, infer, and imagine what lies beyond, but we may never experience it directly. The boundary between the observable and the unobservable is a limit not only of physics but of perspective. It's the point where curiosity meets the unknown, where imagination becomes the only tool left. And yet that limitation gives our knowledge meaning. The fact that there are parts of the universe we can't see doesn't make the parts we can see any less real. It simply places them in context. Everything we've learned about the cosmos, from the structure of atoms to the shape of the cosmic web, comes from the small sphere of light we inhabit. Within that narrow window, we've discovered laws that seem to apply everywhere, from the smallest particle to the largest cluster. Those laws may extend infinitely outward, governing regions we'll never observe. In that continuity lies a kind of reassurance. The universe beyond our sight follows the same rules as the one we know. Still, the idea of infinite continuation remains both humbling and haunting. It suggests that the observable universe, with its 100 billion galaxies, might be only a fraction of all that exists. Somewhere beyond the edge of visibility, entire galactic superclusters may be forming, others fading, their light forever out of reach. Space itself may stretch endlessly, filled with patterns too vast for even our most powerful instruments to glimpse. The universe may have no center, no edge, and no end, only horizons that shift with time, marking the limit of what light can tell us. If you could step beyond that limit, crossing from the known into the unseen, you wouldn't feel a boundary. You'd simply continue moving through space, watching galaxies fade behind you as new ones came into view. The horizon would move with you, always surrounding you, always marking the distance light can travel since the beginning of time. Every point in space carries its own horizon, its own limit of the visible. The universe doesn't end, it continues everywhere, each point containing its own version of everything. Beyond the observable lies not emptiness but continuity, a vast expanse that may be infinite, or simply too large to measure. It's the part of the cosmos we'll never see, yet it's also part of our story, the unseen foundation beneath the world we know. To think about it is to face the limits of perception and the boundlessness of existence at the same time. The horizon isn't a wall, it's a reminder that there's always more. Beyond it lies the rest of reality, unreachable, invisible, but still there, expanding quietly into eternity. When we try to understand the universe, we almost always begin by comparing sizes. We talk about how large something is, how far apart things are, how small we are by contrast. We imagine light years and diameters, parsecs and galaxies. We think in terms of bigger and smaller, near and far. But there's a quiet flaw in that way of thinking. Scale is not a property of the universe, it's a property of how we perceive it. The cosmos doesn't think in meters or miles or years. It doesn't know what big means. Scale is a kind of illusion, a human framework we use to translate the infinite into something our minds can grasp. When you look at a mountain, it feels enormous because you can see it towering above you. When you look at the moon, it seems small, even though it's thousands of kilometers across. A galaxy, even one containing hundreds of billions of stars, looks like a faint smudge in a telescope. The difference isn't in the objects themselves, it's in the distance and in your perception. The mind doesn't experience size directly, it experiences proportion. Everything is measured against something else, against the body, the hand, the eye, the memory of what feels close and what feels far. In that sense, big and small aren't features of reality, they're feelings we attach to perspective. This illusion deepens the farther we extend our view. The Milky Way seems unfathomably large, but compared to the universe, it's a speck. Yet compared to a single star, it's vast beyond measure. The same comparison works inward. An atom seems unimaginably tiny, but relative to the nucleus inside it, it's enormous, and the nucleus itself is a world of smaller particles. Every time we zoom in or out, the pattern repeats. Each level contains another, and between them lies an ocean of difference in size, but not in importance. The universe doesn't assign meaning to scale. It treats every structure, from quark to cluster, with the same physics. There's a strange comfort in realizing that. It means that being small doesn't mean being insignificant. We measure our worth by size because it's the only language we have for comparison, but in the fabric of the cosmos, everything participates equally in existence. A galaxy and a grain of dust both obey the same laws of motion. The same gravity that holds the Earth in orbit around the Sun also holds electrons in orbit around atomic nuclei, in a way that reflects similar mathematical harmony. The universe scales itself, but the rules never change. When astronomers describe the size of the universe, they use numbers that stretch beyond comprehension. Billions of light years, billions of galaxies, each containing billions of stars. But those numbers, as precise as they sound, don't create understanding. They only mark the boundaries of imagination. You can multiply as many billions as you like and still you won't feel it. Our minds aren't built to hold quantities that large. What we can hold is relationship, the feeling of one thing nested within another, the pattern of repetition that carries through every level of reality. If you could watch the universe from outside, if that were even possible, you might not see something immense. You might simply see pattern and motion. The filaments of galaxies in the cosmic web would resemble neural networks or river deltas, their shapes repeating at smaller and larger scales. The galaxies themselves would seem like swirls of light, each made of smaller swirls of stars, each star surrounded by planets and dust, each particle in those worlds following the same physical laws that govern the larger structures. You'd see recursion rather than scale, symmetry rather than hierarchy. The illusion of scale also shapes how we think about time. A human life feels long in the context of years, but short compared to the age of the Earth. The Earth's history feels vast until you set it beside the lifetime of stars or galaxies, yet even billions of years are short compared to the time it would take for light to cross the visible universe. We describe these durations as if they were levels of importance, but the universe doesn't know short or long. Time, like space, simply is. The boundaries we draw around it are conveniences, ways of orienting ourselves within an unbounded process. Consider that from the perspective of a photon, a particle of light, time doesn't pass at all. From emission to absorption, it experiences no duration. For light, the distance across the universe happens instantaneously. For us, it takes billions of years. Which version is correct? Both, depending on where you stand. The difference between them isn't in the universe, but in the frame of reference. Scale, in this sense, applies not only to size, but to perception itself. This relativity of scale appears in the mathematics of physics as well. Einstein's theory of relativity showed that space and time are not fixed backgrounds, but flexible relationships that depend on motion and gravity. The faster you move, the slower time passes for you relative to someone else. The stronger the gravitational field, the more space and time warp around it. Even fundamental measurements like length and duration depend on perspective. The universe doesn't provide an absolute ruler or clock. It provides consistency in the way things relate. When you understand that, the illusion of scale becomes easier to see for what it is. A story we tell ourselves to make sense of something that doesn't require stories. The universe doesn't organize itself into categories of small and large, brief and long-lasting. Those categories belong to us. They help us locate ourselves, but they don't describe the truth of things. From the universe's point of view, if such a thing could exist, there is only motion, energy and change repeating across every level. Even our tools of measurement are extensions of that illusion. We build telescopes to see the vast, microscopes to see the tiny, and clocks to divide time into moments. Each instrument extends the reach of our senses, but each also reinforces our human scale. We measure what fits our ways of perceiving. The universe, however, doesn't need our measurements to exist. Its structures form and evolve according to physics that remain indifferent to observation. Whether something is a nanometer wide or a million light-years across, it unfolds according to the same rules. Sometimes when we call something huge, what we really mean is that it exceeds our ability to imagine it. The distances between galaxies, the number of stars in the Milky Way, the span of time since the Big Bang, these are not huge in the universe's terms, they simply are. The concept of scale breaks down when confronted with infinity. There's no smallest, no largest, only continuums of form and motion. We carve the infinite into pieces so we can talk about it, but those pieces are only abstractions. The cosmos doesn't know it's vast. It doesn't know we're small. It simply exists in a state of dynamic balance, with everything playing its part. This realization changes how we think about meaning. If smallness and largeness are illusions of perception, then so is insignificance. We often look at the night sky and feel overwhelmed, dwarfed by the scale of it all. But the universe isn't comparing. The same laws that shape galaxies shape the atoms in our blood. The same balance between gravity and motion that holds stars together holds us upright on this planet. Every living thing, every particle, every force participates in the same system. The distinction between cosmic and human is one of scale, not substance. Even our language about the universe carries traces of the illusion. We talk about expanding space, as though there were something outside it into which it grows. We talk about edges of the observable universe, as though there were a boundary to cross. We imagine small particles as though size were an inherent quality, rather than a relationship between energy and distance. These words make the cosmos sound like a place filled with things of different sizes, when in reality it's a continuous field of relationships. In quantum physics, this becomes literal. The smallest scales we can describe, Planck length and Planck time, mark the limits of where our current theories can operate. Below those limits, the distinction between large and small, between before and after, may cease to make sense. At those scales, space and time might not be continuous at all. They might be granular, or probabilistic, or something entirely beyond our language. The illusion of scale collapses completely there, because there is no longer a framework in which to compare one size or duration to another. When you step back again to the larger scales, clusters, superclusters, and the cosmic web, the same effect occurs in reverse. Distances become so great that causality itself starts to break down. Galaxies move beyond one another's horizons. Light can no longer bridge the gaps. The relationships that once defined structure begin to dissolve. The concept of distance loses meaning when connection is no longer possible. On both ends of the spectrum, the very small and the very large, scale ceases to describe anything real, And yet, within the human view, scale feels unavoidable. It's how we relate to the universe, how we give it context. The trick isn't to abandon it, but to see through it, to understand that it's a lens rather than a truth. The same stars that seem impossibly far are made of the same matter that makes up our bodies. The same patterns that shape the cosmic web appear in the branching of trees and the firing of neurons. The universe repeats itself endlessly, translating its laws across all magnitudes. Once you see that, the boundaries between scales start to dissolve. The illusion of scale, then, isn't a deception. It's a perspective, a way of navigating complexity. It reminds us that size and distance are relative. That meaning depends on where you stand. The universe is neither large nor small, neither near nor far. It's a single, continuous process. Energy unfolding through time and structure. We carve it into scales so we can understand it, but what it really offers is connection. Every part of it, from the smallest particle to the largest cluster of galaxies, participates in the same unfolding story. For all the ways we've mapped, measured, and imagined the universe, there's one thing we can never quite remove from the equation: ourselves. Every observation, every theory, every image of the cosmos is filtered through the lens of human experience. We are small creatures trying to understand something without size. We use numbers, instruments, and words to reach for the infinite, but what we find, more often than not, is our own reflection staring back at us. The human measure defines how we know the universe, and it shapes what we mean when we say we understand it. Our measurements are extensions of our bodies. The meter was once defined as a fraction of the Earth's circumference, later redefined by the distance light travels in a fraction of a second. The second itself comes from the ticking of atoms. Every scale we use, from microscopic to cosmic, is built on systems that begin with human perception. Our eyes see only a narrow band of light. Our ears register only certain vibrations. Our minds compress time and distance into manageable concepts. Even our instruments, though they stretch our reach, remain designed for the human frame. They turn signals into images, data into color maps, vibrations into sound. No matter how far we extend our senses, we bring the universe back into the shape of human understanding. This doesn't make our knowledge less true, but it does make it partial. The universe as it exists is not the same as the universe as we perceive it. The cosmos has no need of our categories, no need for seconds, kilograms, parsecs, or the word galaxy. Those are our inventions, our handles for holding what cannot be held. They allow us to translate something infinite into something we can think about. Without them, we couldn't speak of the universe at all. But with them, we risk mistaking our models for the thing itself. When we describe the Milky Way's size or the age of the universe, we use numbers that feel almost abstract. 100,000 light years, 13.8 billion years. We say them as if they were simple facts, but each of those values represents a scale so far beyond direct experience that it becomes symbolic. We can't feel 1 billion years the way we can feel a minute. We can't imagine 100,000 light years the way we can imagine a road or a river. What we call understanding at that scale is really translation, a conversion of incomprehensible immensity into forms our minds can handle. This human measure is both limitation and strength. It's limitation because it confines us to the boundaries of perception, but it's strength because within those boundaries we've built a language that reaches astonishingly far. We can't stand outside the universe, but we can describe it with precision from within. We can measure the age of starlight, predict the future of galaxies, and trace the history of matter back to its earliest form. We do this not by escaping our scale, but by refining it, by building systems of logic that allow small minds to model vast realities. That ability is one of the rarest things in the known universe, a consciousness aware of its own limits, yet capable of imagining beyond them. Our understanding of the universe has always mirrored the tools we've used to observe it. early civilizations watched the stars with naked eyes, building calendars and myths to make sense of their patterns. For them, the heavens were a living realm of gods and signs. When telescopes arrived, the heavens became a landscape, something that could be charted, measured, and studied. Later, spectroscopy turned that light into chemistry, revealing that the stars were made of the same elements as Earth. Radio telescopes opened in visible wavelengths, letting us see the Milky Way's spiral structure and the cosmic background beyond. Each new tool expanded not just our reach, but our sense of place. The more we saw, the more we understood that we were not at the centre of things, and that the universe was not built for us. That realization is often framed as humbling, and it is, but it's also empowering. To understand that we are small in scale is not to be diminished, it's to be precise. Our planet is tiny, but it's a place where matter has organized itself into consciousness, where atoms forged in stars have learned to look back at their origins. That's not a reduction, it's a revelation. The human measure doesn't reduce the universe to our size. It brings the universe into focus. Through it, we turn incomprehensible distances into stories we can tell, equations we can solve, and truths we can share. In a way, the human measure is what gives the cosmos meaning at all. Without beings capable of perception, the universe would still exist, but it would have no witness. Its beauty would be unobserved, its order unrecognized. Meaning doesn't arise from the stars themselves, but from minds that can see them and ask why they shine. The act of observing, of asking, turns the universe from an indifferent process into something experienced, something alive in awareness. We are the part of the cosmos that contemplates itself. When you think about the Milky Way, it's tempting to imagine it as something out there, distant and separate. But it's not. You are inside it. Every atom in your body belongs to it, born from the same cycle of creation and destruction that fuels the stars. The calcium in your bones, the carbon in your cells, the oxygen you breathe, all of it was formed in stars that lived and died billions of years ago. You don't just live in the galaxy, you're made of it. To measure the Milky Way, then, is to measure something that also measures you. The relationship works both ways. The galaxy gives us the elements that make us possible, and we, in turn, give it awareness. Without consciousness, the Milky Way is only motion and light. With consciousness, it becomes story and perspective. The human measure translates the physics of the cosmos into meaning. It turns the random into the comprehensible, the indifferent into the beautiful. It's what allows us to see the night sky not as chaos, but as pattern, not as darkness, but as depth. Of course, the human measure is not perfect. Our senses evolved for survival, not for cosmology. We see only a narrow slice of reality. We can't perceive ultraviolet light or radio waves without instruments. We can't feel the flow of time across billions of years. We live at a scale where gravity seems weak, where quantum effects are hidden, where the vast and the tiny both lie outside intuition. Yet somehow, through imagination and mathematics, we've reached across those limits. We've built theories that describe what no one has ever seen directly. We've looked into the past through light, into the heart of atoms through equations, and into the future through models of expansion. Our minds, bound by biology, have extended into dimensions nature never required us to explore. That expansion of understanding is part of what makes the human measure extraordinary. It's not static, it evolves. Every new discovery recalibrates our sense of proportion. When Copernicus moved the Earth from the centre of the universe, the human measure stretched to include motion. When Einstein unified space and time, it stretched again to include relativity. When quantum mechanics revealed the strange behaviour of particles, it stretched once more to include uncertainty. Each time we thought we had reached the limits of comprehension, and each time we found that the mind could go farther. In that sense, the human measure is not about scale at all, it's about translation. It's how finite beings make sense of the infinite. It's the bridge between what is and what can be known. Every map we make of the universe, every chart, every image, is an act of translation, turning something vast into something we can understand. Even the most abstract physics is a form of storytelling, a way of expressing the patterns of reality in human terms. And yet, for all our progress, there are still mysteries that remind us how provisional our measure is. We don't know what dark matter is, though we can see its effects everywhere. We don't know what dark energy is, though it shapes the universe's fate. We don't know what happens beyond the cosmic horizon, or what lies before the Big Bang. These unknowns aren't failures, they're the sign that there's always more to learn. The horizon of knowledge moves outward as we do, but it never disappears. When you look at the night sky and feel that mixture of wonder and distance, what you're really feeling is the tension between the human measure and the cosmic scale. The stars remind you of how small you are, but they also remind you that you can see them, that your mind can hold their light, can think about their distance, their history, their physics. That capacity for thought is what connects you to them. The Milky Way is immense, but in seeing it, you become part of it in a new way, not just physically but consciously. We sometimes say the universe is indifferent to our existence. Perhaps that's true, but indifference isn't the same as absence of meaning. Meaning is what emerges when awareness meets the world. The human measure is the point of contact between the cosmos and consciousness, where the vastness of reality passes through the narrow channel of perception and becomes experience. The night sky is not just light travelling through space, it's light arriving in a mind capable of wonder. In the end, the human measure is not a flaw in understanding but the condition of it. It's what allows us to know anything at all. We may never see the whole universe, but we can feel its shape through the tools we've built and the questions we ask. The act of wondering is itself a kind of measurement, not of distance or time, but of awareness. The universe measures itself through us, and we in turn measure ourselves against it. In that exchange lies something deeper than comprehension, a sense of belonging. From the smallest particle to the farthest galaxy, everything participates in the same reality. We are part of that continuum, not separate from it. The human measure doesn't diminish the universe, it connects us to it, reminding us that the same forces that govern stars also give rise to thought. To look out at the Milky Way and feel wonder is to complete a circle, the galaxy perceiving itself through the eyes of one of its own creations, and in that moment, for all the limits of perception, the scale of the cosmos and the scale of the self become one and the same. Between the galaxies there is a kind of silence that doesn't exist anywhere else. It's not the quiet of an empty room or a still forest. It's a silence so vast that even the word quiet seems too small for it. The space between galaxies is the loneliest, most isolated environment we can conceive of. Millions of light years of near total emptiness, a gulf so deep that even light takes aeons to cross it. Yet this stillness is not nothing. It's a field, a structure, a medium through which everything moves. It's the quiet fabric that binds galaxies together while keeping them apart. If you could drift there, in the intergalactic void, you would find no stars, no dust, no planets. The nearest galaxy would be a faint smear of light, far off in the distance glowing against the endless black. The temperature of the space around you would hover just above absolute zero, about 2.7 kelvins, the residual warmth left over from the Big Bang. A few stray atoms of hydrogen would drift by every few cubic meters. They would pass unnoticed, silent markers of a medium so thin it might as well be nothing at all. Yet in that almost nothing, the structure of the universe takes shape. Intergalactic space is not a vacuum in the absolute sense. It's filled with dark matter, with diffuse gas, and with the faint traces of radiation that still echo from the universe's beginning. Galaxies move through this space like ships on a black ocean, their gravity carving subtle currents in the surrounding void. Filaments of gas and invisible matter stretch between them, linking clusters together across hundreds of millions of light years. From a distance, the universe's structure appears delicate, like lace or frost spreading across a window. But in between those filaments lie enormous voids, regions so empty that a cube of space 100 million light-years across might contain only a handful of galaxies. These voids define the cosmic landscape, giving the universe its shape through absence as much as through presence. It's tempting to think of those voids as nothingness, but they're not empty of meaning. They are the background against which everything else exists. The galaxies we see are islands rising out of a vast dark sea. Their brightness and their motion make sense only in contrast to the silence that surrounds them. That stillness is what allows structure to form, just as silence allows music to exist. Without the spaces between galaxies, there would be no pattern, no order, no motion at all. If you could watch the universe from a great enough distance and speed up time until billions of years passed in moments, you'd see the galaxies drift apart, carried by the expansion of space. The filaments would stretch, the voids would widen. Gravity would continue to bind clusters together locally, but the universe as a whole would grow more diffuse. Over trillions of years, the light from distant galaxies would fade until it could no longer reach one another. Each group of galaxies would become its own isolated island universe, surrounded by deep and permanent darkness. The stillness between them would grow until every island drifted alone, with nothing beyond its own faint light. Even now the process has begun. The Milky Way and Andromeda, along with their smaller companions, are bound together by gravity. But beyond our local supercluster, the expansion of the universe accelerates. The light from distant galaxies already redshifts beyond detectability, stretched by the expansion until it disappears into the background. The space between galaxies grows larger every second. It's a strange thought that even as we look deeper into the universe, the very structures we're studying are moving away from us faster than we can ever reach them. If you could somehow pause the expansion and simply drift in the void, you would notice another kind of stillness, the absence of reference. In that deep space there is no up or down, no sense of movement or direction. The stars of any nearby galaxy would be so distant that they'd provide no fixed point to orient yourself. It would feel as though motion itself had stopped, though in truth you would still be carried along by the expansion of space, moving with it like a leaf floating on an invisible tide. Time would feel meaningless there. Without nearby stars or planets to mark its passage, there would be only the slow, eternal presence of the dark. And yet, even there, in that deepest silence, the laws of physics remain the same. Light still travels at its constant speed. Gravity still curves space. The faint traces of background radiation still hum softly through the void. Even nothingness has structure. Quantum fields ripple everywhere, creating fluctuations that can never quite reach zero. Virtual particles appear and vanish. Energy flickers at the smallest scales. The void between galaxies is not dead, it's potential, the quiet, steady hum of the universe itself. The stillness between galaxies also carries history, the radiation that fills it, the cosmic microwave background, is the cooled remnant of the universe's first light. It has travelled for nearly 14 billion years, crossing through every cluster and every void, filling space with a soft, uniform glow. It's the oldest signal we can detect, and it reaches everywhere equally, even into the darkest corners of the intergalactic void. That faint warmth is the echo of creation itself, a whisper from a time when everything was dense, hot, and bright. It's strange to think that the emptier spaces are also the most ancient, the places where the universe's memory still lingers most clearly. Galaxies occasionally send emissaries into this emptiness. High-energy particles called cosmic rays travel through intergalactic space, sometimes for millions of years, before striking a distant world or detector. Photons from supernovae and quasars streak through the void, carrying messages across unimaginable distances. Even gravity waves ripple through it, faint distortions in space-time caused by the merging of black holes or neutron stars. The void may be still, but it is not silent in the absolute sense. The universe continues to speak across it, in faint signals that persist long after their sources have faded. When you look at the night sky and see the stars, it's easy to think of space as filled with light. But in truth, most of the universe is dark. The bright points we see are rare exceptions. Between them lies a darkness so deep that it defines the cosmos more than the light does. We live in a universe where emptiness outweighs matter by an overwhelming margin. The visible galaxies, planets and stars make up less than a fraction of a percent of the total content of existence. Everything we know, everything we can see, is surrounded and separated by the stillness between galaxies. That stillness is also what gives us perspective. It's what allows us to understand distance, motion and change. If space were crowded, if galaxies filled every direction, we'd have no sense of contrast, no sense of isolation or motion. The emptiness is what defines the structure, just as silence defines music or rest defines rhythm. The stillness between galaxies gives the universe its shape, not by what it contains, but by what it lacks. Sometimes thinking about that silence can feel unsettling. The idea of vast distances, of permanent separation, of light that will never arrive, stirs a quiet sense of melancholy. Yet there's something peaceful about it too. The universe's stillness isn't absence, it's equilibrium. It's the natural state of space when not disturbed by stars or heat or gravity. It's the background that allows all other things to happen. The light of galaxies, the life of stars, even the existence of planets. All of it is temporary motion against the steady backdrop of this calm. If you could listen to the universe, to all its sounds, the birth of stars, the collisions of black holes, the expansion of space, and then strip away everything transient, everything local, what would remain is this stillness. It's the constant hum of being, the faint residue of creation that persists after everything else fades. It's what connects the beginning to the present, what links every galaxy, every cluster, every atom. In that sense, the stillness between galaxies isn't a void at all. It's the quiet heartbeat of the cosmos, steady and unending. As time passes, that stillness will only deepen. Stars will burn out, galaxies will merge and fade, and the universe will continue to expand. In the far future, when even the last stars have died and the galaxies have dimmed into cold remnants, all that will remain is the dark, a universe dominated by the quiet between things. Yet even then, the laws of physics will still hold. The geometry of space will still exist. Energy will still ripple faintly through the void. The stillness will remain, not as an end, but as a continuation. The universe returning to its simplest state. Pure space, pure silence. And here, within that vast calm, we exist for a brief moment, surrounded by light and motion. The stillness between galaxies is what allows everything else to happen, including us. It's the blank page upon which the story of the cosmos is written. And though we live on one small point of light, orbiting one star among billions, the silence between galaxies belongs to us too. It's the space our light travels through, the distance our thoughts imagine, the emptiness that holds everything together. When you step outside at night and feel the quiet between the stars, you're feeling the same stillness that fills the universe. It's not cold, not indifferent, just vast, waiting, and infinitely patient. It's the reminder that all movement happens within stillness, and all sound fades back into silence. The galaxies drift, the stars burn, and in between them, the universe breathes, steady, silent, and eternal. If you were to look at everything we've explored, the galaxy, the universe, the unimaginable distances, the dark between things, and then slowly pull your mind back toward home, you'd notice that nothing truly separates one scale from another. The Milky Way, the cosmic web, the horizon of the observable universe, they're all part of a single unfolding continuum. Wherever you stand, you're standing inside it. The atoms in your body, the light from the stars, the gravity that binds galaxies, all of it exists in the same fabric. The universe isn't somewhere else far away in the cold of space. It's here, right now, in every breath, every photon, every moment of being. The boundary between the infinite and the intimate doesn't exist. The two are the same. When people look up at the night sky, they often describe the experience as humbling. The sight of thousands of stars scattered like frost across the darkness makes us feel small. Yet smallness only exists as a matter of comparison. The scale of the universe doesn't reduce you, it includes you. The light you see from those distant stars is made of the same energy that fuels the cells in your body. The particles that make up your thoughts were born in stars that lived and died long before the Earth existed. The universe isn't out there. It's within you, operating at a smaller scale but following the same laws. The patterns of galaxies, the flow of rivers, the firing of neurons, they're all different expressions of one process, unfolding everywhere at once. We often imagine the cosmos as something vast and detached, but its presence is constant and immediate. Every moment of time, every point in space, participates in the same expansion that drives galaxies apart. The air around you, the ground beneath your feet, the light falling through your window, all of it is part of the same ongoing event that began nearly 14 billion years ago. The Big Bang isn't an event locked in the past, it's something still happening, still echoing, still expanding through everything. Every particle of matter carries its motion, every moment carries its consequence. The universe is not a distant spectacle, but the medium of existence itself. The light that reaches your eyes at night began its journey long before life existed on Earth. A single photon from a star 1,000 light years away might have left its source at a time when humans hadn't yet begun to dream of civilizations. And yet, that photon travels across the vastness of space, through the stillness between galaxies, through dust and magnetic fields and gravity, until it finally strikes the back of your eye, triggers a chemical reaction, and becomes part of your perception. The light of the universe literally enters you. The act of looking connects you directly to the cosmos, not symbolically, but physically. When you see starlight, you're participating in the exchange of energy that has shaped the universe since its beginning. Here, in the quiet of a single human life, that immensity can seem abstract. We live on timescales that barely register against cosmic ones. A lifetime is a flicker compared to the life of a star, a breath compared to the history of the universe. But the length of time doesn't determine its importance. Within that flicker lies awareness, a brief but conscious reflection of the cosmos upon itself. The universe has existed for billions of years without knowing it existed. Then, for a brief moment, on a small world orbiting an ordinary star, matter began to think, to feel, to look back at the stars and wonder what they were. That moment is still happening every time you look up. Science can describe the processes that led to this. How matter cooled, how gravity formed galaxies, how stars forged the elements, how planets coalesced, and how life emerged. But describing it isn't the same as feeling it. Understanding the mechanics of existence is different from realizing that you're part of them. When you breathe, you exchange atoms that were once part of ancient stars. When you drink water, you consume molecules older than the Earth. Every element that makes you up, carbon, calcium, iron, was built in the heart of a star that lived and died before the sun was born. You're not separate from the universe. You're a continuation of it, organized for a while into the pattern called human. Even the smallest actions, seeing, breathing, thinking, are manifestations of universal physics. When neurons fire in your brain, They follow the same laws of electricity and magnetism that guide lightning through clouds and radiation through space. The warmth you feel from sunlight is the same energy that powers the stars of distant galaxies. The rhythm of your heartbeat echoes the balance between contraction and expansion that defines the cosmos itself. In a literal sense, you're made of the same materials, governed by the same principles, sustained by the same forces. The boundary between you and everything else is a matter of perception, not substance. There's something grounding in realizing that. The universe may be vast, but its vastness isn't foreign. It's the context in which everything happens. The fact that we can think about it, that we can form ideas about galaxies and light years and quantum particles, means that the universe has reached a point in its own development where it can understand itself. Consciousness is not an accident of isolation. It's the product of connection. Every thought you have is powered by energy that was born at the beginning of time. Every idea is a configuration of particles forged in ancient stars. When you think about the cosmos is thinking about itself. The human mind often divides the world into categories, here and there, large and small, near and far. But those distinctions dissolve when you look closely enough. The atoms in your body are the same as those floating in distant nebulae. The laws that govern galaxies also govern your DNA. The heat that drives a star is the same type of energy that makes life possible. There's no true separation between the individual and the universal. The universe expresses itself in galaxies, in planets, in oceans, and in minds. Every form is temporary, but the process continues without end. This sense of continuity can change how we think about time. We often treat the present as a fleeting moment, sandwiched between the past and the future. But on a cosmic scale, there is only now, an endless sequence of transformations, each one giving rise to the next. The past still exists in the light of distant galaxies, travelling through space toward us. The future already exists in the expansion of the universe, unfolding according to the same principles that have always governed it. When you look at the night sky, you're not seeing the past as something gone, you're seeing it as something still happening, still connected to your moment of looking. The present stretches across billions of years and billions of light years. It's not a point, it's a continuum. The Earth itself is a condensation of that continuum. Every rock, every drop of water, every cell is a record of cosmic history. The minerals in the crust trace back to ancient stars. The air you breathe contains atoms that have cycled through countless forms, through oceans, plants, animals, and the bodies of other humans. Life on Earth is not an isolated event. It's a localized expression of universal chemistry. From that perspective, the boundary between the cosmic and the personal disappears. The stars above you and the ground beneath you are part of one continuous system, still evolving, still connected. If you could see the universe not as separate things, but as one event, a single, vast unfolding, you'd notice that there's no outside. Everything that exists is inside it, part of the same process. The galaxies are not suspended in space, they are part of space. The stars don't burn in isolation, they're powered by the same physics that fills every cubic centimetre of the cosmos. Even the dark matter and dark energy that shape the universe's evolution are part of that same unity. They're not hidden substances, but aspects of the same field of existence. When you strip away the distinctions, what remains is one continuous reality, here, now, and everywhere. That reality includes all scales. From the smallest quantum fluctuations to the largest clusters of galaxies, the same fundamental principles apply. Energy and matter, space and time, are different expressions of the same underlying order. Einstein's equations describe how mass and energy shape the curvature of space, and that curvature defines the motion of everything within it. On the smallest scales, quantum mechanics describes probabilities rather than certainties, a reminder that the universe is not static but dynamic, always in flux. These aren't abstract ideas. They're the patterns that govern everything from your heartbeat to the orbit of planets. Sometimes, people imagine that science strips the world of mystery, reducing it to formulas and forces. But the opposite is true. Understanding how the universe works doesn't make it less beautiful. It reveals the depth of that beauty. Knowing that the stars are powered by nuclear fusion doesn't diminish their light. Knowing that galaxies form through the slow pull of gravity doesn't make them less majestic. In fact, the more we understand, the more miraculous the ordinary becomes. The warmth of sunlight, the fall of rain, the shimmer of a distant star, all of it becomes a reminder that the same laws that shape galaxies also shape this very moment. The phrase, "the universe within," isn't a metaphor. It's a literal description. Every cell in your body contains the chemical history of the cosmos. The iron in your blood, the carbon in your DNA, the oxygen in your lungs, all of it came from processes that began long before the sun. The atoms in your body are billions of years old. They've been part of other stars, other worlds, other forms of life. They've travelled across time and space to become you for a while, before continuing their journey elsewhere. You're a brief configuration of matter in motion, a momentary pattern in the flow of the universe. That thought could feel transient, but it can also feel liberating. It means you're not separate from the cosmos, not apart from its story. You are the continuation of a process that began with the first expansion of space. You are part of the same unfolding that drives galaxies and births stars. Your existence is not small, it's precise. You occupy one place, one time, within an unbroken whole. The universe doesn't happen around you, it happens through you. In the grand timeline of the cosmos, our species is new, barely a flicker in the history of light. Yet within that flicker, we've learned to see almost to the beginning of time, to map the structure of the universe, to decode the laws of nature. That ability is astonishing. Out of the billions of galaxies, in a universe filled mostly with silence and darkness, a small species on a small planet developed the capacity to understand where it came from. For all the vastness of space, consciousness is one of the rarest things we know of. It's how the universe wakes up. That awareness doesn't make us separate from the cosmos, it makes us its expression. The universe isn't just matter and energy, it's also perception, reflection, curiosity. Those too are natural phenomena. When you look at the night sky and feel awe, that feeling is part of the universe's response to itself. When you wonder about the future, about what lies beyond the cosmic horizon, that wondering is the universe exploring its own possibilities. Every thought, every question, every spark of imagination is a continuation of the same story that began with the first burst of light. If you let yourself imagine the universe, not as a cold expanse, but as a living continuum, a process rather than a place, it changes how everything feels. The galaxies aren't distant, they're extensions of the same fabric you inhabit. The space between stars isn't empty, it's filled with the same fields and forces that sustain you. Every second that passes carries within it the history of everything that came before. You don't exist apart from that, you exist because of it. The phrase, here, now, and everywhere, isn't an exaggeration. It's the simplest way to describe what's true. You are here, a particular point in space and time, conscious and alive. You are now, a moment in the long unfolding of the cosmos, temporary but real. And you are everywhere, made of the same matter, moving with the same expansion, bound by the same gravity that shapes galaxies and stars. There is no distance between you and the universe because you are the universe, organized for a while into thought and experience. Even in the quietest moment, when the world feels still and separate, you are moving, turning with the Earth, orbiting the Sun, spinning with the Milky Way, drifting with the local group through the Laniakea supercluster, carried along by the expansion of space itself. Every breath you take is part of that motion, Every heartbeat vibrates within it. The universe doesn't just surround you, it includes you in its every movement. To exist at all is to be woven into its flow. And when you lie down at night and close your eyes, the same universe continues. The atoms that make up your body hum with the same quantum energy that fills the void between galaxies. The light from ancient stars still travels across the dark, eventually finding its way to some other world, some other being looking up in wonder. The motion never stops, and neither does the silence that carries it. Here, now, and everywhere, the universe continues, vast and intricate, silent and full of meaning, still expanding, still unfolding, still becoming itself through everything that exists, including you.